So hi, everyone. Welcome to the Causal NLP tutorial at EMNLP 2022. This tutorial is hosted by myself, Zhijing, Amir, and Zhang. So here are our co-organizers of the tutorial. And during the tutorial, we'll mainly answer two types of questions. First, what is causality? And second, how can causality help NLP? So now let's start. First, we will set the expectations for this tutorial. For things to expect, the entire tutorial will be into two parts. The first part will last about half of the time, and then we will start with a motivation, go into statistical view about causality, added with NLP examples. Then we will do a round of Q&A. In the second part, we will focus on causality for better NLP models. And we will cover topics such as interpretability, robustness, and fairness, and ending it with another QA. So our tutorial contents are also based on the poll that we have conducted a while ago with 149 votes, where we surveyed people's interests in this tutorial. So we'll cover all these points that are mentioned here. Then we will start with the slogan of this tutorial. We are organizing this mainly because we really learned a lot from causality, and we believe causality makes us more insightful NLP researchers. And the benefits of causality could be seen from many different aspects. The top three in my mind is that we can use it to build better models. We can use it for deeper understanding about the real world with larger social impact, as well as improving our scientific practice. So we will first start with the vocabulary that we will use in this tutorial. So we will distinguish two different concepts. The first one is causality in the real world. An example question could be in traditional causality, people try to address things like, does smoking cause cancer? Or when it moves to NLP questions, it could be, does gender directly affect citations? How does Twitter sentiment affect COVID lockdown policies, and so on? And these correspond to tracks such as NLP applications, CSS, linguistic theories, and so on. So apart from the real world causality, we will also see the other part, the orange part, which is causality of language model behavior, such as which neuron affects what in the language model. How does the model capture the data generation process? Or why do certain why do certain prompts work? So the difference here, if we simplify the two parts, the difference here is that on the left, you'll see a lot of real world variables, such as smoking, cancer, and so on. But on the right, in the causal graph, we'll see language model as one of the causal graphs, or properties of language model as one of the causal variables. So our two parts of the tutorial also correspond to the real world causality and the language model causality. The connection here could be that a lot of tools that we use in the statistical models of causality can also be applied when we are analyzing language models. So now we'll dive into the first part. What is causality? I'll start with a motivation. So a lot of people have heard that correlation does not mean causation. Imagine we have a common sense data set or news data set with a sentence, as ice cream sales increase, the rate of shark attacks sharply increases. And then we might plug this into a model and see what will it infer from this. The first hypothesis could be that, okay, now I see ice creams maybe make swimmers taste better. However, the other hypothesis could be it's about getting warm. So when the weather is warmer, then people tend to eat more ice cream and people tend to go swimming more, thus providing the possibility for more shark attacks. Using this example, we will dive into the causal graph and its terminology that we will use throughout the tutorial. So again, this example is from getting warm. Its direct impact are two ways. First, eating more ice creams. Second, more people swimming in the sea. And then swimming in the sea further lead to more shark attacks. And then the first thing we'll see here is that usually when we draw the graph, you have seen that we keep the direction. So if the topological order when we're drawing causal graphs means that causes always go before the effects. It could be from left to right, or it could be from top to down. So this is a practice when drawing a causal graph. Moreover, let's see more graph terminologies. So if we see a part of the graph, such as A causes like A direct link to B, it means like A directly causes B, or A is a parent of B, B is a child of A. The other case could be A causes B causes C. In that case, we would say that any causal variables that are before a certain variable are ancestors. So A is an ancestor of both B and C. Similarly, we define descendants. So B and C are descendants of A. Now we dive into more vocabulary. So apart from knowing the relationship, we will now look into the structure of more variables. If we consider the case of 3 variables, then we will see these 3 common examples. First is a chain causal structure where A causes B causes C. The second is a fork structure, or you can say A is a confounder of B and C. The last one is a very interesting one. It's called V structure or collider. A is the collider of B and C. So what do these terms mean? Like how does it connect to our current research? One important implication of this is the definition, is how we talk about spurious correlation. For example, in the fork structure, when A is the confounder of B and C, here we could give an example such as a certain way to collect a data set causes the label distribution and also the distribution of a lot of spurious features. Then we would say that B and C are spuriously correlated. One example case would be the word not largely correlate with the label negative in a lot of data sets. The other case would be in the V structure, we will see another type of spurious correlation. It's given A, B, and C become spuriously correlated. So when we are trying to formulate correlation and causation, we know the statement that correlation does not mean causation. In this specific case, if we give names to all of these variables, A, B, C, and D, we would say that they are in a connected causal graph. So there's a pool of variables. And in a lot of cases, all the nodes in a connected causal graph may be correlated. However, if we use the principle of taking any 2 of the variables like B and D, we couldn't say B causes D. Well, then the question becomes, can we go further? We really want something causal. So the hope is that with additional intervention or with causal discovery methods, we would be possible to conclude phenomenon such as C causes D. This will also be the emphasis of our following tutorial. How do we move from statistical observation of the data to causal conclusions? For a more formal formulation of this, we could say that correlation basically is a statistical dependency between X and Y. And causation is defined as when you actively do an intervention on X. If you see Y change correspondingly, then X is a cause of Y. And then we will also note that the intervention will only change the target variable, but not directly changing other variables. So This is a definition of intervention that we will use later in the tutorial. Now we will dive into the overview of statistical causality as our part 1. So first we will have an overview about the steps to learn causality. As we might see from the previous graphs, the actual step how general scientists, even in natural science domain, discover causality is through the steps as follows. First, they try to understand which variables are of concern in this setting. Then the second step is to understand what affects what, namely form the graph with directed edges. And all of these are into the area of causal discovery. Then after we know the causal graph, people might be interested in the properties of each edge. Some of the properties would be, if I change X by 1, how does that affect Z? Or it could also be some more complicated statistical properties about how changing X affects changing Z. And the final goal for all scientists would be, are we able to even have a deeper understanding of the entire mechanism, how this causal graph, causal mechanisms work? And that helps the human civilization to advance. I also really like this quote by Democritus. He said that I would rather discover one causal law than be the king of Persia. So given the 4 steps we have mentioned, I also want to mention that the full stack causal learning, like the whole process, is very challenging. It takes generations of scientists. So usually the practice to break it into sub-problems, which will also be the structure of this tutorial. So in this statistical introduction of causality part, we will break it to causal effect estimation and causal discovery. For the causal effect estimation part as the first sub-problem, what we will do is that we put the blue part as our assumption. For example, many domain experts already suspect several causal graphs. Then based on that, we will do the effect estimation. And now I will give the stage to my co-organizer, Zhang. The way we'll conduct this part is that he will lead the statistical introduction, and I will plug in NLP examples after each important concept.
Hello, everyone. Thank you very much for the lovely introduction, Zhijing, and thanks for making the slides so beautiful. So actually, I would like to go back a little bit. Because so right here, you can see here in both cases, at the very bottom, B and C can be dependent, right? In the first case, B and C are dependent without giving A. And in the second case, B and C are dependent giving A. But very often times, we cannot really clearly see that. Let me give an example. So if you consider different documents or different domains, right? You can see style and content, roughly speaking, are somehow dependent, right? So are they confounded because of the common cause, or are they dependent because we are considering different categories because of the selection? You can see in many situations, we can see dependence, but we want to see the underlying process. And actually, the 2 situations are correspond to very different ways if you want to correct this kind of spurious correlation. Okay, think about it, right? They are dependent. And selection bias are almost everywhere. If you work with the data collected on internet, clearly you have selection bias, right? So the definition of selection bias is as follows. Where the data point is included in the sample depends on the value of some of the features, right? So if this is the S variable, selection variable, now if S is 1, it's in this data set. If S 0, then this data point is not in this in this document, or sorry, in this data set. Then you can see this is almost everywhere. So please pay attention to this 2 different kinds of spurious correlation. And later you can see we try to deal with some of the problems. But first of all, the causal perspective really helps us understand the underlying process, right? And at least we know what's going on and we know how to do correction. Even in some situations, we cannot really discover everything about the underlying process. We can still benefit from this view, right? If you have a clear mind, you know what to do, and you will not simply consider different kinds of dependence in the same way. Okay. So as Zhijing just mentioned, this part is about kind of statistical aspect of causality. Essentially, we want to discover there are two fundamental tasks. One is to how to make use of data given the causal structure, right? I know because of my background information, I know X causes Y, and I would like to see how X influences Y, right? I want to identify causal effects, or I want to do counterfactual reasoning, right? So given a particular data point, a particular document, how can I do counterfactual reasoning? And this is also related to, say, data generation, because when you want to generate a new data point, you want to follow the causal process, right? Especially when you try to do counterfactual generation, you have to follow the causal process and change only those things you can change. The second part is about how to discover the information structure from data. And this is known as causal discovery or causal representation learning, depending on the context. So now let me start with the first problem. So let's see how we can identify causal effects or how we can do counterfactual reasoning. Essentially, currently in AI, at some level, you can see we care about the three types of problems. Here's the setting. Usually in machine learning, we are given data set, right? We're given data set, a sample for some variables, and then we want to make prediction. In some other situation, we also need to have access to the causal graph, as you can see from here. So in the first problem, essentially the prediction problem. So you would like to see, for instance, would a person cough if we find or see that she or he has yellow fingers? And then in this case, clearly don't care about the graph. You just rely on this conditional probability, right? You can use the deep learning method. You can use the logistic regression, whatever method to solve this problem. You just want to make optimal prediction, right? When you just care about the optimality, there's no truth. You only care about optimality. However, in the other two problems, you care about the truth. In the second problem, you want to answer the following question. Would the person cough if we make sure he or she has yellow fingers? So by using the term make sure, essentially you want to do interventions. You just make sure that this person has this feature, and then you want to see what will happen to whether person coughs. And right here, let me see. Yes, here by make sure, I mean we do intervention, right? The definition of intervention, as Zhijing mentioned, is as follows. Intervention is a particular type of change in the system. If you intervene on, say, yellow fingers right here, then you can only directly change this variable. You have to leave all the other variables in the system the same as before. This way, since only this guy changes, right? Then if there's any difference in another variable, you know, oh, this variable must influence that variable. Right? This is how you can verify causality or discover causality by making use of interventions. And here, you want to, in other words, you want to see the interventional effect of X2, yellow fingers, on X3, cough, right? So this is the causal effect. So you just want to see whether the intervention on one variable will make a difference in another variable. And you want to quantify it with this probability. And this probability looks like a regular conditional probability, but this is actually causal effect. It's a causal effect X2 on X3. But sometimes we can have kind of simpler description of the causal effect. For instance, you might want to take expectation. Then this is average causal effect, and so on. This is the second problem. You want to see the interventional effect or causal effect of some variable on some other variable. Right here, basically, when we just look at the population, it's about the whole population, right? There are no individual. And then we can go to another level. Now let's try to answer the following question. We have a structure, right? We have data. Would George, a particular person, cough had he had yellow fingers, given that he does not have yellow fingers and coughs? So here now you can see it's another level. We are talking about a particular unit, particular subject, right? And clearly, whenever you talk about a particular subject or subgroup, your answer would be more informative, right? It's more specific. And now you can, and also you make use of evidence. Something happened to George, and you can make use of such information, right? So this is the basic about the personalization or how we understand each other. When we try to understand each other, we make use of what we observed, and we try to understand the underlying hidden features of the subject or unit, and then we give more specific answers. Later, you can see how we can answer this question. Basically, those two questions really are causal questions, right? And you have to rely on the causal picture, causal structure, if you want to answer them. Without the causal picture, we cannot answer two questions at all, because even with the same joint distribution, but the different causal structure, the answer could be totally different. Okay, so.
Yeah, I supply an NLP example, right?
Oh,
Yes.
Okay, perfect.
Great. So I really like how Kun lays out the idea. One little thing to emphasize is that when I myself learned intervention versus counterfactual, it can be very confusing a lot of times. One key insight, as Kun has mentioned, intervention is population level, a group of people. Think about randomized control trial over two groups. And counterfactual is over a specific instance. Moreover, some people might have the question why, like we say contradictory things. George had yellow fingers, and given that he does not have yellow fingers. So this is actually based on, we take out a real world example of George who did not have yellow fingers so far, and then force the property to be on him. So that explains this sentence. Now I'm going to add some NLP examples or examples related to NLP to supply these cases. The first case I would supply is prediction. Basically, anything that shows correlation among the data is the first example, like it's the first type. So one example study that we have conducted is to check how does the gender portion relate to different areas of research. So basically, you crowd a data set of different research areas like NLP, HCI, and so on. And then what you will see here, the percentage is the percentage of female researchers on Google Scholar. And then the nature of this whole graph, or many graphs with this nature, is the correlation between female and a certain domain. So given domain D, the probability distribution of female. And as we know that this does not mean causal relations, such as NLP is easier for female researchers than signal processing is. There's no evidence for that so far. The other thing we can see, maybe we'll see even more like aggressive conclusions, such as if we collect a data set of papers and they have different attributes of the papers, such as the first author's gender, last author's gender, and so on. We might also see statistical dependencies, such as given the last author being a certain gender, the first author is more likely to be what? So some specific example we can see is if the last author is female, then the first author is 2 times more likely to be female as well. These all, as we mentioned, are correlation, pure statistical dependency. Another example to supply this will be when we're analyzing language models. If we have a sentence such as "my friend is a doctor," then the masked entity will be try to predict a pronoun following this. Then we have different choices for the pronoun. And then probably we'll see the language model giving us different prediction probability. Given doctor, the probability of he, she, they, and so on. So this also reflects the correlation that language models captured, not necessarily causation, which is more of the center of fairness problems. The last example I will add in from NLP is counterfactual. What does that actually mean? So as we mentioned, the difference between intervention and counterfactual is that counterfactual is on the unit level. So we take an NLP model input, such as my friend got an MD degree, medical doctor degree, and pronoun will become a doctor. So the quantity of interest fits in the form of counterfactual in that given the same MD degree or all other conditions, how much will gender affect the possibility to be a doctor predicted by the model? So as in the graph, we might see maybe gender correlates with MD with some unknown causation. And then the things we're interested in is how much gender affects the occupation doctor. And we try to solve it by counterfactual, at least in this unit level. So these are the NLP examples, and I'll give it back to Kun.
Thank you. Wow, this is really novel. So the first problem we want to solve is identification of causal effects. Now, this part is kind of mathematical. So essentially, you want to find this probability, so probability of recovery given the treatment, right, or given different values of treatment. So this is the kind of very general way to measure causal effect. Of course, as I just mentioned, you may want to find expectation or some other features of this conditional probability. The standard way to find this causal effect is to use the randomized controlled experiments, right? You have two groups, right? Across the two groups, you have to guarantee one thing. All the remaining features relevant to recovery should have either the same value or the same distribution, right? Given that I can, in one group, I can just use treatment A, in the other I use B. In some situations, we have control group and treatment group, right? Since all the other features actually are the same across the two, they either have the same value or the same distribution across the two groups, then if you see a difference in recovery, clearly it must be because of the different treatments, right? So this is one way to discover causal effect by making use of randomized controlled experiments. Of course, you can see if you can do so, it's nice. You can have some quantitative measure, but this method clearly has some drawbacks. First of all, it's really hard to achieve that. How can you guarantee that all those remaining features have the same value or the same distribution across different groups, right? And in many situations, there could be a lot of common causes. There could be a lot of hidden features. You don't even have access to them. How can you guarantee that they have same value or the same distribution? That's one problem. Second, even if you can do so, you can see the difference, right? You can measure the causal effect, but you may not have the concrete description of the causal mechanism regarding how treatment influences recovery, right? You don't have the functional form. And in many situations, you will really want to see the functional form, and you want to see how treatment and other features jointly determine recovery, right? So, and this question can be answered by making use of causal discovery and the quantitative causal model estimation. Good. Now, let's.
Yeah. So I want to add in a little bit illustration of why Kun mentioned that RCTs are very helpful. In the same time, it could be expensive. An NLP case that I have seen is that there are papers illustrating mental health counseling. And then the causal question they want to answer is, how does different conversational strategies affect successful counseling? So we will see that the ideal way that people want to do it is to get all the patients with mental health deficiency, split it into random group 1 and random group 2. For random group 1, implement a certain conversational strategy. You can measure it by the counselor's linguistic properties. And then group 2 is the control group. Then you record the recovery rate of conversation style 1 and recovery rate of conversation style 2. The difference is then the average causal effect of how strategy affects recovery. But as we know that especially patients like mental health patients, it could induce ethical issues if we try out different conversational strategies with risks. Some of the cases, just to complement this RCT style, some of the cases could be less of a concern, but these are just special cases within MT, like within machine learning, but not generalizable to real world cases that much. So in machine learning, sometimes we want to measure how does a certain data property or how does a certain training setting affects the performance. One example case where we can do RCT is that in one of the studies, we explore what affects the machine translation performance. And we suspect that in the training set and test set, whether it's original language A to translate to language B or vice versa, the direction of translation needs might matter. In that case, we did go through the randomized control trial similar setting, observe a large drop when we shift the alignment between the training set and the test set. And then also on the other direction, we observe another drop. So this is some cases in machine learning where we do have control of RCT. And then we will dive into more examples where we don't have full power to do experiments, but we'll rely on observational data.
Okay, cool. So first of all, here you can see a very kind of famous example to illustrate Simpson's paradox problem. Here, suppose we have is a real data set. So we have two groups of patients with kidney stones, and for one of them they have small stones, and for the other they have large stones. We have two groups, and for each of them, as you can see from the two columns, treatment A is better because the recovery rate is higher, right? So for the group with small stones, it's 93% versus 87%. And for the patients with large stones, the recovery rate is 73% versus 69%. So A is better, right? Now, if you merge the data, all of a sudden you can see B seems to be better. The recovery rate is 83% versus 78% in the other group. So for the other treatment. Now comes the question. Suppose you are the doctor, and suppose you only care about the recovery rate. Now you have a new patient. Would you recommend A or B? Would you recommend A or B? You only want to recover, maximize the say recovery rate, right? A. Sorry. Yeah, but so it's a new patient, right? You don't know kind of which group the patient is from. So would you A? Okay, A. B? B. Wow, it's almost a tie. Okay, very good. So good. Now you can see why I call it paradox. If you know the patient is from this group, then you would recommend A. And if you know the patient is from B, you would recommend A again, right? Now, basically for some of you, A or A is B because stone is either small or large, right? Why do we have this issue? Basically, this is because when we talk about this, the last row shows the dependence between treatment and recovery. In this case, you can verify that the stone size is actually a common cause for treatment and recovery. That's the case. And the last row just shows the dependence or correlation, right? And the dependence can be almost arbitrary because of this common cause. The dependence does not show anything about the causal effect. But whenever you make recommendations, you only care about one thing. It's a property of this causal link. You want to see, you don't want to change this part, right? It's given. You just want to see how treatment changes recovery, right? That's the only property you care about. So you focus on this link, and the property of this link, known as causal effect, can be totally different from correlation or dependence. That's why. So the answer clearly should be A, right? Because I just care about this part. And then you can see, oh, if you fix the stone size, A is always better. Clearly, I would recommend A. And even if I don't know stone size, later you can see we are going to recommend A. So this is the example to illustrate the big difference between causal effect. Yeah. Okay, so about sample size, you can think of, yeah, oh, okay. So the question is, how you can do the comparison if the two groups have very different sample sizes? Is that the question? Yeah. So basically, it's a statistical problem. Now, let's just ignore that part. Why? Because first of all, you can say sample size is not very small, and you can even think of a lot of data points here. So this could be say 7, 9, 7, 8, 9, 7. 81, 87. Okay, 81, 87, say 1,000. You can have a very big number, but you can still see exactly the same phenomena. Just ignore that kind of random error part. Consider the asymptotic situation. Then we can just focus on the underlying problem, right? So for now, I would say, imagine the sample size is very large, but the same phenomena will happen. Now you can see from the, actually you mentioned the sample size. From the number of data points, you can see stone size and treatment are clearly dependent. I have to use this. So stone size and stone size and and the treatment are dependent. For small stones, for the patient with small stone, it's more likely for them to be in group 2, right, to receive treatment B. And for those with light stones, it's more likely for them to receive treatment A. So they are dependent. That's why I have this link. And that's also why I said that this guy, stone size, is a common cause for treatment and recovery. Okay. So now, given this, is there an answer to your question? Did I answer your question?
Yeah, so I feel like so basically like the twist here, like why you're like A or certain B. It's because like
So like the group 1 and group 3, and they have drastically different number, right? The base number, the sample size. So if you basically increase it to, for example, both to 263, and I think the marginal, like the successful rate should be like A over B, right? Because like that's what I want to say.
Actually, exactly. Later you can see a illustration. That's exactly why.
Oh,
so
okay.
Yeah, wonderful.
Oh, sure.
Yeah.
Yeah.
Okay, good. Now we want to see the causal. There's another question.
Yeah, so I was just trying to understand is this like example of how the Simpson paradox impact the causal effects? Because this really make me feel like the subgroup size really could impact the final conclusion.
For now, I would say please just ignore the sample size. Mm-hmm. Why? Because when I talk about different data points here, I just want to illustrate that they are dependent. As long as they are dependent, as long as this guy is a common cause, we have this issue. Mm-hmm. Of course, if you want to see whether they are really dependent, you have to make use of data points, right? Observation, the sample, right? So that's why. Is that answer to your question?
Yeah, I mean, this just remind me of the Simpson paradox.
This is just, yeah, exactly. This is Simpson paradox, yeah. And there could be, this is a real data set actually. And there could be a lot of other examples. You are totally right. Wonderful. So now, yeah, Zhijing, could you? Sorry, wait a second, because those online cannot hear you.
Hello, am I audible now? Yeah. So if the sample size is very small, let's say 80 or 87 as compared to 260 and 270, how are you confident about the percentage, 93% or 69%? Is the confidence comes into picture there to find the causality here?
I didn't quite get it. Could you?
So
I said, yeah, probably it's the same question, right? If
no, it's a little different in the way, like how confident you are about that 93% of treatment success rate. Yeah, statistical confidence.
Maybe you can repeat it, Zhijing?
He's mainly asking about the statistical confidence about the 90 something percent.
Okay,
yeah.
Wonderful. That's a statistical problem. For now, at the beginning, I said ignore the sample size thing. Suppose the sample size is large, very large. Now we can just depend on, if you have a very large sample, then you just care about the kind of population version, right? Oh, they are dependent. They are dependent. That's it. They are dependent. They are still condition dependent. So ignore the kind of relatively small sample size here. Let's focus on the distribution. Is that good? Because in order to solve a problem, first of all, you have to consider population version, and then if you have some guarantee, you can consider the finite sample size version, right? So now let's go with it. So you want to see the causal effects right here. Of course, if you care about the dependence, as you can see from here, you rely on the conditional probability, right? Essentially from here, you can see the conditional probability of recovery given treatment. And you can see, or if you rely on the conditional probability, B is better. That's for sure. Now we are doing something different. As I just mentioned, you want to see the causal effect of treatment and recovery, you have to do intervention. Essentially, you care about this conditional probability of a recovery given the intervention on treatment. And now, remember the definition of intervention. If you do intervention, if you do intervention on treatment, you directly change this variable, only this variable, and you have to leave all the remaining variables in the system the same as before, at least for the moment, right? So now if you do that, you directly set this guy to either A or B. In other words, the original causal mechanism for this guy for treatment will disappear, right? That's intervention. You directly change the value of this variable. and then the original causal mechanism will disappear, meaning that there are no link here. They will be independent, right? If you do intervention, they will be independent. And then if they are independent, you can just make use of the kind of statistical rules and you can find this probability. The only difference intuitively here, in order to find this causal effect, the only difference is to replace the conditional probability of stone size given treatment with the marginal distribution of stone size. Because now stone size and treatment are independent. You just use the marginal to replace the conditional. Of course, later I give more general situation, while you consider more general situation. For now, you can see the underlying idea or underlying principle for you to answer this question. Oh, this is the only difference. Once I do that, everything's statistical, right? Causality, only this part of causality is about the definition of intervention. That's all. So now you can see basically, now you can see intuitively why it works. So this is right here, I have two treatments, we have two groups, right? And here, so two groups of patients. For those with small stones and large stones, you can see A is always better, but here you have more data points. This is sample size, right? That's why they are dependent. And here you have more data points, here you have more data points, as you can see from there. And if you consider average, essentially the sample size will play a very important role. So if you consider average, clearly the final average corresponding to treatment B will be closer to this guy. And the final one for treatment A will be closer to this one because you have more people here and more people here, right? As a consequence, you can see, oh, after you take the average, B seems to be better, right? That's conditional distribution. You can see it, and this is the conditional distribution because you have to consider this conditional, you have to use this conditional distribution to do marginalization. Now, if you do causal effect identification, you use this one instead. You use the same distribution across the two treatments. You use marginal distribution because once you do intervention, treatment and stone size will be independent, following from the definition of intervention. Now you do averaging, and then this would be the final causal effect identification problem. So this is the expectation with respect to the conditional probability, as you can see from here. Clearly, A would be better, right? So this is just a causal effect. Now you can see why. You have to you have to apply intervention virtually, and then you can just derive a causal effect. Although you don't really do intervention because here we only make use of the observational data. So this is a setting of identification of causal effects. Sometimes it's also known as observational studies of causal effects, according to Dana Rubin. Why? Because you have to access two things. First, you have a causal graph. Second, you have some observational data, and then you can see how X influences Y. Okay, so this is the basic setting of identification of causal effects. So if you want to give a principled answer, first of all, you want to consider this issue. Given a causal graph, and given some of the values of some of the observed variables, right? Or some variables are observed, as you can see from here. In some situations, you may not observe stone size. You only observe those two variables, right? Now, the first thing is whether the causal effect of treatment and recovery is actually identifiable. So if it's identifiable, it means the following thing. I only know the causal structure, and I only know the distribution of the observed variables, right? I cannot observe those hidden variables. In that case, if actually you have different underlying models, causal models, do you always end up with the same solution? If the answer is always the same, we say, oh, the causal effect of treatment and recovery is identifiable, otherwise not. To illustrate that here, let's look at this example. So this is another example to illustrate the Simpson paradox. Let me explain it. Here, we are considering X size and a cholesterol. So generally speaking, you can see for each age group, the more X size you do, the less cholesterol you are going to have on average, right? That's very good. So basically, we should do more X size. You can see they are negatively correlated. And here, if you consider each of those age groups, it's very clear. However, in a very similar way, if you ignore the age information and only consider the distribution of X size and cholesterol, clearly they are positively correlated, right? As you can see from here, they are positively correlated. So what that mean? It means that the more exercise you see, the more cholesterol you are going to see on average. It's not a causal term anymore. It's not a causal effect. Now, you want to identify the causal effect of exercise on cholesterol, right? And suppose you don't observe age. Now you can see with the same distribution for exercise and cholesterol, you can have different models. In one case, so exercise on right here, the effect of exercise on cholesterol might be very small, and this guy age actually has very kind of huge effects on both of them. This is one way to explain their dependence. Alternatively, I can have another model. So the exercise on cholesterol is kind of very big. At the same time, the age as the common cause has a very small influence on both of them. And both situations can produce exactly the same distribution of the measured variables, and they follow the same structure. Now you can see basically with the same structure which is given and the same distribution of the measured variables which is given, you may have different answers because the two influences are very different. So intuitively now you can see in this case, if you have a latent compounder age here and only observe the distributions for those two variables, then the causal effect of exercise on cholesterol is not identifiable, because you can have different answers depending on the underlying true causal model, right? So why do we have this issue? Again, it's because what we can observe is limited. We may have this causal structure. Later you can see we may not want to trust this structure. That's why the second part is about how to discover structure. For now, let's take it for granted that structure is correct. And you only have a distribution over the measured variables, and you want to identify causal effects. And you can see in some situations it's not identifiable. Now you want to see the criterion to verify whether causal effect is identifiable. So there are some famous criteria. Let me just quickly explain two criteria here. The first one, the backdoor criterion, proposed by Yuda Pearl from UCLA and Peter Spertis from CMU and other people. So the name is very, very clear. Backdoor criterion essentially is a graphical criterion. Different from this, Daniel Rubin from Harvard actually advocated the potential outcome framework to see whether causal effect is identifiable. So they make use of ignorability or strong ignorability, conditional ignorability thing to verify whether kind of causal effect of X and Y is identifiable. They are slightly different. I don't want to emphasize the difference. Essentially, a graphical one could be more intuitive. That's why here, to save time, let's just use the graphical criterion. Suppose this is a graph. You can see a lot of variables here. We say Xi, Xj, ordered variable pair, satisfies backdoor criterion if the two conditions are satisfied. The first one says that no node in Z is a descendant of Xi. So as you can see from here, if X6 is in the set of variable Z, then this is violated. The second one says that Z set of variables blocks every path between Xi and Xj that contain error into Xi. That's why it's called backdoor criterion. So Z blocks all those backdoor paths into Xi. For instance, here, if Z is X3 and X4, do you think the backdoor criterion is satisfied? Just try to verify the two conditions. So if Z is, now we are talking about Xi and Xj, and we want to see whether Z satisfies the backdoor criterion relative to Xi, Xj. Okay, we have two conditions. What if Z is a set of X3 and X4? Do you think backdoor criterion is satisfied? The first condition, first of all, is the first condition valid here? No node in Z is a descendant of Xi. Yes or no? Is that true? Clear, right? That's true, because only descend X6 is not there. It's good. Second, do you think Xi, X3, and X4 block all those paths into Xi? All paths between Xi and Xj and into Xi? Yes or no? So clearly, right, all those paths will be essentially Xi and Xj. We can consider different paths. This path, this path, this path, and this path. Right? In total, there are only 4 paths. And clearly each of them is blocked by X3 and X4. So in this case, we say Z satisfies the backdoor criterion. Later, you can see how we can proceed. What if Z is the set of variables x4 and x5? The same thing will happen. So all those 4 parties will be blocked. And what if Z is x4? Sorry? Do you think this one blocks all those parties? No? Which one is open? Which one is not blocked? Wonderful. Sorry? Which path is? I cannot hear. X3? Oh, yeah, the path. Which path is not blocked? You can see the path. Well, path is basically a concatenation of different causal edges. So now, what if we have this one, right? Xj, X5, X2, 4, 1, 3, Xi. This M shape. This one is not blocked because X4 is a collider here. Given collider, only collider, this path will be open. This is about deseparation and whether path is blocked. So it's another thing. Now, this one is open. It's not blocked. So we say if Z is X4, then it does not satisfy the backdoor criterion for Xi and Xj. Okay, good. So you can check the condition. If you have the graph, you can easily check whether backdoor criterion is satisfied. And if that's the case, you can immediately find the causal effect of X on Y. So if Z satisfies the backdoor criterion relative to X, Y, now the causal effect of X on Y can be written this way. Sometimes we say probability of Y given X hat, or sometimes we say PY given do X. It's the same thing, just a causal effect. Different people use different notations. Now, basically the idea that follows, I can just make Z and X independent because I do intervention on X. I just replace, if you compare this causal effect, PY given X hat, with the conditional probability of Y given X, the only difference is to replace the conditional distribution of Z given X with the marginal distribution of Z. That's all. This is called backdoor adjustment. In many cases, you may have common causes, right? For instance, here, if you ignore all the variables, X4 will be a common cause for Xi, Xj. And if you have access to X4, clearly the backdoor criterion is satisfied, and you can find the causal effect of Xi on Xj by making use of X4, as you saw from here. Right here. Actually, if you observe this guy clearly satisfies the backdoor criterion from treatment, for treatment and recovery, because this guy blocks all paths between the 2 variables and into this variable, right? And then if that's the case, you can immediately identify the causal effect by making use of this rule, this adjustment rule. Oh, this is the first case, a typical one. It's called backdoor criterion. Good. So it's a graphical criterion, and then if it holds true, you can immediately solve the problem. Later, I will explain another one very quickly called front door criterion. You can see they are very intuitive because you just make use of a graph and you can see whether the condition holds true. Zhijing, maybe you want to give examples?
Great. So as we have mentioned, Kun is a very hardcore statistician. And now I'm going to adding a little bit context to NLP. So this is the track of CSS and NLP. So basically the action that the model is doing, the causal question we're interested in is when COVID just happens, I wonder what's the role that NLP community could play. So we look into a causal problem about what are the causes for lockdown policies. And then the NLP data we can have are social media data. The traditional tool we can use is to have a BERT classifier to get the sentiment from social media. The hypothesis is that even if there are some cases with severe COVID cases, would the governor still open a state if people show very emotional sentiments on the internet? So the causal graph here is that the COVID cases affect both the sentiment and the lockdown policy. It's a much more simplification for the complicated graph we have seen before. And in this graph, we already satisfy the backdoor criteria by blocking COVID cases. So I will quickly go through the data collection part. So basically, people could have 1 trillion tweets about COVID, get the sentiment, also collected the COVID cases day by day and get the social distancing policy strictness. Then with this data, we form into this graph where the confounders, mainly the COVID cases, are this variable here. It causes the sentiment, causes the policies. And then the association we want to effect is already given the case numbers, can we see the direct effect from the maybe angry sentiments on Twitter on the social distancing policies change? As we have mentioned, directly doing intervention, we don't have that ability. So we block the backdoor pass. In any 3 variable case like this, blocking Z satisfies the backdoor criteria. So we apply this statistical estimate and implement that in Python. A pseudocode of this will be iterate over every data point you have and record the case number, change the sentiment from positive to negative, see the difference of the policy over them. So this is a rough implementation pseudocode for this. And then given all these estimates, we are able to get the direct effect over all different states. The top ones are Colorado, Massachusetts, Florida, Texas, and South Dakota. Great. And in the remaining part, we will speed up a little bit so that we can cover both causal effect estimation and discovery. Go ahead. That's a very great question. So in this case, or generally, people try to, maybe let me repeat the question so that online attendants can listen. So the question is, how do we assume this causal graph is true? And we try to add in all domain expertise to add the confidence of this causal graph. First, the COVID data is before the policy, 14 days before the policy. So time constraint only allows one possible causal direction. The other is that in the actual study, we list out much more confounders. So there are 10 plus confounders. It could be possible that people can add more. This is sort of the assumption that we take for now. Yeah, I think the question is a very good motivation for the second part. I do very much agree on this. So the more confidence the domain experts have, the more more confident we are with the final effect estimation. If the domain experts are not confident, then it will be introduced in the second part. We will use causal mechanism, causal discovery to find the actual causal graph. Very great question.
Indeed, that's really a good question. Actually, a lot of researchers in causal discovery shared the concern. That's why in the 1980s, some people at CMU started working on causal discovery. So how can you really discover information from data, right? Very good one. We'll come back to that point later. So now let's have a very quick look at the front door criterion. Just have a look at this graphical representation. You may have a confounder here, latent confounder for X and Y. Again, you want to identify the causal effect of X on Y. Now we have a confounder. Then if you don't have Z variable, clearly the causal effect of X and Y is not identifiable, as you can see from the Simpson paradox, right? But if you have Z here, you can see this is the front door variable. Then all of a sudden, you can still identify the causal effect of X and Y. Intuitively, essentially, you just apply the backdoor criterion twice. Here, you can see the effect of Z on Y, and then you can see the effect of X on Z, and then you put them together, you can identify the causal effect of X on Y, as you can see from this adjustment rule. You apply backdoor criterion twice, you can find the causal effect of X on Y. Okay, so intuitively, this is the front door criterion. You can see Y. You may have compounder, right? But Z, basically, the Z set of variables is in the front door path from X to Y, okay? And here you can see an example. This is a very bad example because it's artificial. It was given by kind of some company, to do something that is not very kind. Basically, this is a story. They want to see whether smoking has a very bad effect on, say, health, right? Lung cancer. And then in that case, that gave the data. Say, oh, genotype may be a common cause for smoking and lung cancer. And here you have TAR, right? Clearly TAR should be here, right? According to the domain knowledge. Now, based on the information, based on, I know we cannot directly measure genotype, but we can measure those 3 variables, including smoking, TAR, and lung cancer. And then you can just apply the backdoor criterion or backdoor adjustment rule to estimate the causal effect of smoking on lung cancer, as you can see from here, for different values of X, smoking, not smoking, and you can just find the probability distribution of Y. And then you can see, oh, basically, smoking does not have a better effect according to the data. Of course, the data is fake. They try to say that smoking does not have a better effect. But in any case, you can see, you can really identify causal effects if you have the structure and the data for some for the measured variables, if the causal effect is identifiable. Okay, cool. Now let me spend maybe 5 minutes. I think we have 5 minutes. Remind me if it's too long. On counterfactual reasoning. So remember, we have the last question in kind of artificial intelligence involves counterfactual reasoning. Here, let me give a kind of more abstract example. Suppose we know X causes Y. So for instance, X is the attendance and Y is the grade, final grade for a student. And we know that we have so many data points. We even know the causal model. Y equals log X plus U plus 3. U is noise, is unobserved thing, right? Hidden thing, is noise. So we can see the distribution here. Now, suppose I'm here. For me, my attendance is X, little x, and my final grade is Y. This is the data point corresponding to me. Now, for me, what would happen? What would Y be if X has been X prime? So here, the question is that follows. For me, the same person, what would Y be if X has been another value X prime? So some people may say, oh, here, this is just a statistical problem. I know the value of X, I know the conditional probability, I can just make prediction. This is the expectation of Y given X equal to X prime. Is that true? Or is that a good answer? Now, clearly, this is in this case, it's very simple because we know X equals Y, it's fine. But the problem is, when you do that, you don't make use of any specific property of me. Intuitively, you can see for me, my X value is here and Y value here. I'm so strange because among all those students with the same attendance, my grade is pretty low. Compared to them, my grade is very low, right? This reflects something about me contained by the noise. The noise is independent from X. So here, actually, from this XY value, you have some information about the noise. You may say, oh, even if he attends the class, he may not really pay attention, right? Or maybe I'm dumb. So in any case, you have information about me from this XY pair. And then in the future, when you do intervention on X, that hidden feature of me will not be changed. They are independent. So you can apply the same thing, and then you can just solve the problem. Okay, so this is counterfactual reasoning, and here you can see the precise setting. We talk about the particular situation or unit. U is unit, like me. In which we have observed the values of some measured variables, and then you want to see what value Y would be had X been X prime in situation U. So for me, you do intervention, you want to see the effect, you want to see the value of Y, giving you some observations or giving the information about this particular subject. Okay, so notation is that follows. For you, you want to see the value of Y, given you already set the value of X to X prime. That's it. So now how can we answer this question? So U is not directly observable, but U is an indicator. So we have to make use of evidence. Basically, equivalently, we can put it this way. I observe evidence about a particular subject, and then I want to see the value of Y after intervention. This is the counterfactual question. Okay, here you can see the standard procedure to answer the question. First of all, you want to find the information of the noise term or hidden unobserved features from evidence. Suppose this is a causal graph. Then each variable is, this is the function causal model or structural equation model. Each variable, say Z, is a function of the theoretical causes W and some unobserved factor. noise. Then from the evidence, you can just infer the information of the noise. This is the posterior distribution of the noise given evidence, right? And then you just replace the equation for x by x prime because you do intervention. You force me to say, to have attendance x prime. This is the second step. And then you just make use of this new value of x and this information of the noise to see the value of y. That's it. Why can we do so? It's because this intervention does not change my hidden feature. That's why I can use the U information or information of the hidden features learn from the evidence when I try to answer the question. Now, quantitatively, you can see how we can answer. The answer would be here. Why? First of all, from x, y value, okay, you can see the ultimate value of noise. U hat would be e to the power of y minus x minus 3. And then I can answer this question. I use U hat, the ultimate noise value together with the new value of x. Then this is the answer, as you can see from here. So this is the counterfactual reasoning. It's very useful because it's a way for you to really understand the unique hidden feature of the subject, right? It's not directly given. No other method can directly make use of the information of noise. But now you can infer the information of noise and make use of it in order to make your answer more specific. Okay. Okay.
Great. So we will end this part with a final NLP example about, given all these statistical formulation, how can we apply this back to NLP? This is just a brainstorming part. So one of the example tasks could be, we collect a large data set of papers and again, investigate the counterfactual on gender. And then the question will, at least the example case we look into is the usage of uncertainty expressions, such as this may indicate that, the may. And then the question, if we form it counterfactually, it becomes, if we take out all the originally male authored papers, had the paper and author's characteristics been exactly the same? If we change the gender to female, how much will the target attribute change? So we have some explorations in the following papers, but I also welcome you to take this as a take-home thinking exercise. Here we will have an NLP modeling problem as we take in the text as input. And moreover, this counterfactual directly connect to fairness. So the definition of fairness, there are many of them. One of the court case says that the central question in any employment discrimination case is whether the employer would have taken the same action had the employee been of a different gender, given all the or all the other demographics, and everything else had been exactly the same. You will also see a similar formulation here where counterfactual is essential. Great.
Okay. Thank you very much, Zhijing. I learned a lot about the NLP from you. So good. Now let's have a quick look at the second part. Essentially, let's see how we can discover causal information from data. And in many cases, we may have a lot of hidden variables in the system. And you can see under what condition we can really locate the hidden variables and estimate their relations. So first of all, in order to answer this question, this is very dense. The idea is very clear. You want to see causal information from data. Now we have to answer two questions, right? Why? Because we have to make use of only the data to recover information. First, what kind of property can we discover, or what kind of property in the data is related to causality? In other words, you want to find the footprint of causality in the data, right? So it's the first one. Later you can see how we can really see the footprint of causality in the data, and then we can try to verify it, and then we can recover information. The second question is whether we have identifiability guarantees. So, you know, there's a big difference between causal discovery or causal representation learning and regular machine learning things. Why? Because here you care about not just optimality, but you care about whether you can recover the truth, because the causal process is there, right? So you have to show that if you have enough data, you can really recover the truth. Regarding the first question, essentially, we make use of the very fundamental property of a causal system known as modularity. Here, we have three variables: wet ground, rain, wet ground, and slippery. They are dependent, right? And we have a causal view. We know something generates rain, rain generates wet ground will make ground slippery. We know the causal process. Then modularity says the following thing. All variables can be dependent. I don't care. I can decompose the whole system into a lot of subsystems. Each of them generates one variable from the parents. It's a causal mechanism, local mechanism. And then those local mechanisms are completely irrelevant to each other. Variables can be dependent, but those processes do not share information. Okay, so that means if I change something here regarding how rain causes wet ground, this will not change anything else. Right? Similarly, if I have another way to make it rain, this process or this change will not change anything about this process or that process. The three processes are completely irrelevant to each other. And then, as you can see from this modularity property, you can derive some statistical properties that can be verified in the data. First, you can see that although Z and Y are dependent, they will be conditionally independent given X. Why? Because if you know X, then essentially X will determine all the information Y relative to anything outside this process. And that means no matter what value Z takes, as long as I know the value of X, then I have the same information about Y. Z does not contain additional information about Y if I know the X. This is conditional independence. So from modularity, you can see conditional independent relations among the variables. This is the first condition. Second, when the system may be noisy, here, in addition to wet ground, there might be some other omitted factors, right? Hidden factors. If X and Y do not have other common causes, then the noise term would be independent from X, right? So this is independent noise condition. If X and Y are not confounded, or if they do not have other unmeasured common causes, then the noise term in the causal mechanism will be independent from the cause X. And the last one is regarding kind of non-stationary environment. Suppose now you travel, right? Now you are in Abu Dhabi, you go to other places, and then you can see different distributions for XZ and X and Y, right? You have different distributions. Now you have changes. So essentially the causal model will enjoy the property of minimal changes and independent changes. So by minimal changes, I mean, with the causal representation, you have a minimal you have a changes in a minimal number of causal mechanisms. If you have a wrong one, you may have to make use of more changes in order to understand the same joint distribution. And at the same time, if they change, we know the changes must be independent because they are different modules. They are not related at all. How this part change, this part regarding rain causes the wet ground is completely different, completely independent from how this part, the X to Y part changes. So this is independent changing property. Basically, we have some properties that can be verified with data, right? Okay, this is the first question. In the second one, you want to see what kind of information of causality can be recovered from data, right? Before answering that question, let's see the setting of the problem. Now you can see we can consider three axes of the problem. First, what kind of data do you have? In some situations, we have ID data. We have a single distribution. We have some data points generated from the distribution. And in some cases, we have multiple distributions. And in some cases, we may have temporal information, right? You can have violation of ID data assumption. And the second dimension is whether you have parametric constraints. In some situations, we know it's the relationships are linear. In some other situations, we know it's a kind of something about the conditional distribution. We can always benefit from constraints. The last one is whether you allow a lot of latent components, latent variables in the system. Okay, so here you can see a summary of kind of current methods for causal discovery or causal representation learning. Now, in different situations, you can see you have different results. You can end up with different things or different information of the causal structure or causal representation. Generally speaking, in the ID case, usually you can only end up with the equivalence class. Of course, if you have parametric constraints, you can end up with unique identifiability under some assumptions. But if you go beyond the ID setting, all of a sudden, you can recover the underlying causal variables and the relations in a relatively easy way. I will give examples. So I'll just go use example to illustrate all those results. In the first case, you can see this is the data set collected by my collaborator, Marlene Novak. Her last name is very cool, Novak, just go forward. So very cool lady. So here we have data set. In archaeology, they want to see how or why people from in different areas look different. And they collect a lot of data point, a lot of actually it's 250 skeletons, and then measure 8 variables, including gender, diet, location, weather, cranial size, cranial shape differentiation, and so on. They try to see why we look different. Clearly, in this case, we can only try to see the relations from data, right? Because we cannot do interventions. Here you can see the data, and here you can see the method. We can make use of conditional independent relation in the data to recover information of causality. And typical methods include the PC algorithm and FCI algorithm. PC stands for Peter, Spertus, and Clark Glimmer. The first letters, they are first names, Peter Clark algorithm. So in this method, we assume there are no latent compounder. And then under relatively mild assumptions, you can show that if you have enough data, then the result is correct. Here, let's see how it works. You have data here. From data, you can discover a set of independence or conditional independence constraints. And then you want to find a DAG or a set of DAG to satisfy the set of constraints. That's why it's called a constraint-based method. And here you can see how it works. We start with a complete graph. If the 2 variables are conditionally independent, then we just remove the edge. You can show why. So here they are independent. Okay. And then in this case, x2 and x4 are independent given x1, not x3. Then this is the only way for them to be related to x3. They have to be causes of x3. Otherwise, they share information because x3, without the condition on this guy, they are not going to be conditionally independent. And then you can do propagation. Now you can see, for the relationship between 3 and 5, the direction must go this way. Because if it goes this way, then we are going to have fake V structure. This is known as the V structure, as Zhijing just mentioned. So they are both causes of x3. Now we know the direction must go this way, because otherwise the fake V structure, since x2 and x5 are independent given x3, right? So they are related because of x3. Now we end up with this one. Now we have 2 questions to answer. Given this result, first of all, we cannot determine the direction between x1 and 2 and the direction between x1 and x4. Can we go further? This is the first question. What assumptions allow us to go further regarding determination of causal direction? The second one is, what if the system had a lot of latent confounders? So with FCI algorithm, fast causal inference algorithm, in principle, you can deal with the confounders. And the result, again, is guaranteed to be asymptotically correct. However, the result by FCI is usually not very informative, because whenever it is possible to have a latent compounder there, the method will tell you, yes, there could be a latent compounder. As a consequence, you may discover very few direct causal relations without compounder. Yes? X1 and 5. Actually, I didn't hear last part. Yeah. Oh, you mean okay, cool. So here, the question, if I understand correctly, sorry, I didn't hear you very clearly. So I was saying you assume that conditionally independent given x3. Is that what you mean? Oh, actually, this is what you can discover from data. This is another statistical problem. It's about how you can discover conditionally independent relations from data, right? So you can do statistical tests. Of course, you always have error. You have type 1 error, right? But basically, if you have a large enough sample, then the type 2 error would be type 1, type 2 error would be very small, and you can, with very high confidence, you can trust the result. That's why I always said it's asymptotically correct. Okay. So now let's try to address those 2 issues regarding how you can find the direction and how you can allow a lot of latent compounders. Yeah, it's clear. So this is the result on the data. Now you can see, yes, you can really discover something. Geodistance will influence climate, gender influence the cranial size, and so on. It's cool because by analyzing data with only kind of standard statistical tools, you can really see something behind the data. Okay.
This is a data set we directly collect. So the case where I found these discovery algorithm really helpful is that we actually have statistics about how different scholars behave, and just Google Scholar statistics and their co-author characteristics. Then we try to answer causal questions such as, does the scholars themselves being a certain gender causes their co-authors also tend to be this gender. Or people could also potentially check the diversity innovation paradox or various biases in these real-world data sets.
Okay, now let me show two examples to illustrate whether it is possible to discover whether there are confounders, latent confounders in the system. Very quickly, in the first example, if you apply PC, you get the following thing: 1, 2 not adjacent, right? 1, 4 not adjacent, 2, 4 not adjacent. We have a V structure, we have orientation propagation, it's good. Now the question is whether it is possible at all for you to have a latent confounder right here. Do you think now we can only measure kind of a finite number of variables in the system? Do you think it's possible at all to have this variable, hidden variable C, as a common cause for X3 and X4? Yes or no? Some say yes, right? Actually, the answer would be no. Why? Otherwise, I would not have asked the question, right? So this is because in this case, if you have such a C variable, right, then given X3, this path X1, 3, C, X4 will be open. In other words, you can see if you are given X3, X1, and X4 will not be conditionally independent. They will be dependent because of this influence. So as a consequence, you can see you are very sure that there are no common cause, and you are sure that X3 is the direct cause of X4. This is cool because in some cases you can really easily see one variable is the direct cause of another without any latent compounder. And even in our everyday life, you can just use this. For if X1 is rain, 2 is a wet ground, and 3 is a slippery. You can see, I know X3 does not cause X1, and then I know conditional independence. Then the information is strong enough to conclude that X3 must be a direct cause of X4 without the compounder. Okay, so now let's look at the second example. Here we have independent there. So if you apply PC, you will see something very weird. Let me just show the result. If you apply a PC, you can see X1 clearly is not adjacent to 3 or 4, and so on. And you can find a V structure here, and you can find a V structure here. You have two V structures. That means they are the direction from 4 to 2, and they are another one from 2 to 4. If you apply PC, you will see this kind of contradiction. Why? The only way to explain why is to allow latent confounders. So X2 and X4 are dependent because of latent confounders, and there are no direct causal influence between X2 and X4, definitely. Because if they are the influence from 2 to 4, then X1 and X4 will not be independent, but you observe independence. And again, you can see a lot of examples even in our everyday life. Let me give one. So let X1 be whether I'm sick, X2 be whether I'm in this meeting room, X4 is whether you are in this meeting room, and X3 denote whether you are sick. You can verify that, those independent relations are kind of approximately true given the environment. And then we can conclude that although both of us are in this meeting room, there are no direct causal influence. Then we are here for some reason. What's the reason? Essentially, we have this event or tutorial, right? So you can infer there must be some hidden variable there, and you can try to understand it. Okay, so basically this is part of the FCI algorithm. Now let's go further. We want to find a direction between two variables. And if you are willing to make some rather mild assumptions on the causal mechanism, all of a sudden you can distinguish between cause and effect without making use of time information. So here you can see in the linear non-Gaussian case, you can do so very easily. Let me explain the setting. Here, when I generate the data, X causes Y. I first generate X and then I generate Y. And in the first situation right here, X and noise are uniform, as you can see from here. They are uniform. They are not Gaussian, right? And then if you try to regress Y on X, essentially just try to recover this causal mechanism. The noise or the residual basically would be independent from X, right? Because they are originally independent. Now you just recover the true process. They are independent. But if you do the same thing in the wrong direction, in the reverse direction, when you try to regress X on Y, this is a regressing cause on effect. You have a residual, you have a Y variable here. Now you can see, first of all, they are uncorrelated because by construction of linear regression, residual will be uncorrelated from the predictor. but clearly they are dependent because information of the other variable, second variable, right, given the first variable will be different across different values of second variable. So they are not independent. Now you can see in the wrong direction, you are going to have dependence between the residual and the predictor. Actually, the same thing happens even if you have a very flexible model. The second one is the post-nonlinear causal model we developed a long time ago. So here we have two nonlinear functions. You can see this model is very flexible, but the same thing will happen. And the same thing will also happen to the additive knowledge model because of special case. Now, this is a post-nonlinear model. Effect is a nonlinear distorted version of the nonlinear effect of cause plus noise. Why do we have this kind of two nonlinear functions? It's because the second nonlinear function usually cannot be ignored. It could be sensor distortion or measurement distortion. And in biology, for instance, whenever you use an instrument to measure something, there's a distortion. As you can see, the contain linear models, nonlinear additive models, or even multiplicative noise model as special cases. Now, even for this model, you can really distinguish between cause and effect. You can see the asymmetry between two variables. Here's the illustration. We have two variables. You can see a scatter plot here. And if you assume x1 cause x2, you fit the model, you estimate nonlinear functions, and you estimate noise or residual, they are independent. But in the reverse direction, from x2 to x1, you cannot find the independent residual, as you can see from here. Okay, so that means according to this model, we should prefer the direction from x1 to x2. Actually, x1, x2 are the altitude and the precipitation of more than 300 cities. Clearly, altitude should be the cause. You can really verify that. And mathematically, you can show that in only 5 very specific situations, cause and effect are symmetric in the sense that in both directions, you can find the independent residual. If neither of them holds true, then cause and effect will be asymmetric. You can find the direction. Those 5 situations are very specific. First one is the linear Gaussian case, and so on. So each of them is very specific. And basically, the measure for them to be true, generally speaking, would be 0. In other words, generally speaking, the causal direction between two variables is identifiable, even if the data was generated according to this very flexible model. And of course, if you have stronger assumptions on the model, the direction usually is also identifiable. Okay, this is how you can identify data, the causal direction between two variables without making use of temporal information. Now, let me quickly say something about how to recover latent variables. Let me start with this kind of motivating example. In psychometric studies, very often we use answer scores, right? We use questionnaires and we have answer scores. We know the answer scores are dependent, generally speaking, but they are not directly causally related. By analyzing answer scores, we try to recover the underlying mental conditions and their relations, right? So we want to go to the hidden world with the hidden variables, mental conditions, and their relations. That's it. Now, how can we proceed? In the last 60 years, a couple of methods were developed. Essentially,
yeah, also another motivation from the NLP, since we see a lot of tabular data, just directly connecting it to NLP is that we could say that when we want to analyze a dialogue between people, we can record all the statistics, maybe the speed people are speaking, linguistic properties of their dialogue, and so on. And then the motivation would be, can we discover intent, emotion, personality, and so on, this latent causal graph behind the dialogue?
Thank you. Now, let me just briefly say something about one method published recently, right here. So it's called the Zhijing condition, generalized impact noise condition. Basically, it's just regarding whether combination of some measured variables is independent from some other measured variables. So you can just do independent tests, and then you can verify this condition. And then you can discover two things. First of all, you can see which latent measured variables share the same latent variables as parents. And then you can also find the causal ordering among those latent variables. So here you can see application we did years ago. So this is known as the teacher's breakdown of data. We have 28 measured variables and 500 data points. So apply the method. On the right, this is the hypothesized model given by experts. And right here, you can see the latent variables and they are causal ordering discovered by the method. Basically, they are kind of consistent. So this verifies two things. First of all, the experts basically didn't rely on data. They have very good understanding. Their model is so good because it explains the data. So at the same time, computational methods are very useful because you can really recover all those hidden variables and their relations, right? Without making use of any domain knowledge. Okay. And you can go further. Here, we in those papers, we basically recover the high deep structure, deep latent structure by analyzing and measure the variables. So you can allow a lot of latent variables and you can recover their relations, even if they're you have a deep structure. Of course, here we assume the relations are linear. So we benefited from parametric constraints. And currently, a lot of people, including my group, are working on the general situation. Essentially, you have to make use of parametric constraints in the previous setting. Now, if you allow the violation of ID assumption, all of a sudden, the situation, the problem is easier to solve. Here, we know traditionally we try to estimate time-delayed causal relations. This is what gradient causality is about. In gradient causality, you try to see whether one process is uniquely useful for the prediction of another process, right? And they can say it's causality. Under some assumption, the gradient causality is true causality under some assumptions. And now you can, with the new advances in the field, you can deal with gradient causality or time-delayed causality with instantaneous relations, and you can go further. Let me talk about this setting. Suppose we have video data, right? We can consider video data as a high-dimensional time series. And we assume that video data is an invertible arbitrary nonlinear function of the underlying latent processes. The latent processes can be causally related. The only assumption is that for the latent processes, it must take some time for the causal inference to take place. So for the latent processes, there are no instantaneous relationship, right? We are talking about time series, it's totally fine. So, and then you can show that surprisingly, even if the causal relations among the latent processes are completely non-parametric and the function G is completely non-parametric, you can recover those latent processes without any difficulty. Now, let me just show two very quick examples. The first one is known as the Kitty mask dataset. So here we have a very simple dataset, right, with subjects there walking around, and with this video data as input, we can recover 3 latent processes. It turns out that those 3 latent processes are independent from each other. There are no causal inference, causal relationship between them, and they are just a movement in one direction, movement in the orthogonal direction, and the size of the mask. Very simple, and clearly it's interpretable. And this is a second dataset known as a mass spring dataset. So we have 5 balls with different colors. And between some pairs of balls, you can they are the hidden spring. That's why they are related. Now they just move around. You have the video as input, and this is output of the method. Essentially, they learn the 10 latent processes that are just X and Y coordinates of the 5 balls. It's cool. You just recover the objects in the video without making use of any supervision signal. And at the same time, you can recover their causal relations. So one ball will influence another if they are the hidden spring, if they are the spring between them with some time delay. It's cool. Now you can see this is completely general because you benefited from time constraint or temporal constraint or time information. And then we only have a few minutes left. Let me quickly say something about the non-ID situation. Another non-ID situation. So we may have multiple distributions, right? As time goes on, you can have non-stationary data, or you can have distributions. You can have data set collected under different conditions. Then you have different distributions. One thing I would like to emphasize is that causal modeling and the distribution shift are heavily coupled. If you have a causal model, we know that because of modularity condition, the distribution can change, but the different modules will change independently, right? And then if you have the distribution shift phenomenon in the data, you can try to verify whether a particular causal model or structure is plausible. So in other words, with distribution shift, we can easily solve the problem of causal discovery under some further assumptions. And here, you allow a causal model to change. You can allow causal influence to be stronger and weaker, and you can even allow some causal relation to disappear. Okay. For this one, essentially in this work, we assume they are only a specific type of compounders, and then we can solve the following problems. First of all, for those variables, we can discover for which of them the mechanism changes. And then you can find the skeleton, and then you can find the causal direction by making use of independent changing property, because in the right causal direction, they must change independently. And if one thing does not change, it's invariant, right? It's a special case of independent change because the constant is independent from everything. And then we also visualize how the mechanism represented by the conditional distribution changes over time across different domains. I'll skip this part. As an application of this method, you can do a domain adaptation or transfer learning in an automatic way. From data set, you can discover, you can have a compact representation of how the joint distribution can change across domains, represented by this graph. And then in the target domain, you have values of the features. You can just do inference in the graphical model. So it's a standard way to do adaptation. You make use of information across different domains to discover how things can change. And then you make use of new information to infer the new value of y. According to that pearl, basically this should be a kind of principled way to do adaptation, domain adaptation. Okay, here you can see some result. Clearly the performance, in every paper that says so. Basically the performance will be better. And then one thing I want to say that causal discovery is still very difficult. In this case, you can discover graph from distribution, and you have to make some assumptions so that this recovered graph is causal. Without those assumptions, it could be totally different from a causal representation. Here, let me give one example. Suppose this is the true underlying process. Let Y be disease and X be symptoms. Now, clearly, disease will cause symptoms, right? And you can assign different patients to different clinics according to symptoms. So S is the selection variable. If S is 1, I just send this patient to first clinic. If S2, I send it to a second clinic, right? This is second variable. Of course, I just have this guy. Basically, I do selection based on the symptoms. Now, if you consider different clinics, you can see something very interesting. First of all, across the clinics, the distribution of the symptoms will be different. That's true because I assign patients to different clinics according to the symptoms, right? PX will be different across domains, but PY given X will be the same. It's interesting. Why? Because Y and the selection are independent given X, meaning that the conditional distribution of Y given X and different value of S would be the same as the distribution of Y given X, conditional independence. So now you can see across different clinics, the conditional distribution of Y given X is the same. Then this would be a kind of very economic graph to represent how the distribution changes. Under some assumptions, if you assume there are no selection bias, then this would be the causal graph. But here we have selection. As a consequence, you can see this graph we discovered from data is totally different from the true causal graph. In the true causal graph, disease causes symptoms. In this graph, symptoms seem to cause disease. Why? Because the assumption of no selection bias is violated. So again, causal discovery or causal representation is still a hard problem. Usually have to assume something, right? And the assumption violated, the discovered graph may be a representation of the property of the distribution, but it may be different from the causal representation, true causal representation. Oh yeah, that part will be eliminated. Good. So to give a quick summary, in this part, you can see essentially we deal with the data in a statistical way, and we try to answer two questions. In the first one, we are giving qualitative causal structure together with some observational data for some measured variables, and you want to see how X influences Y. And in some other situations, you want to see how to do counterfactual reasoning or how to do counterfactual generation. Essentially, you make use of the qualitative structure information and the quantitative data information, and then you can answer this question under some assumptions. I briefly touched on the conditions on which you can make it possible. And then I would like to emphasize that it is completely possible to recover causality from data. Recent advances actually gave a lot of stories, a lot of examples. So in some cases, you may want to recover just a causal structure over the measured variables. It's simpler. And in some situations, you may even want to recover the latent variables, latent compounders from observational data. And if you have multiple distributions or temporal data, then this is much easier to do. If you have ID data, generally speaking, you have to assume something about a causal mechanism, or you have to enforce some very strong sparsity constraint. And how can we solve the problem? Essentially, you may want to formulate some technically operational causal principles, and then you can establish identifiability to show that with this condition, I can really recover the underlying truth without any ambiguity. So, okay, this is the end of this part. Now we'll be happy to take some questions.
Maybe the adjustment would be because I have a little bit bonus points in the end. So we could be that I've quickly finished the bonus points, and then during the break, feel free to come to Kun for more Q&A. So here are the bonus points. I'll just quickly reshare the screen. With all these ways to get qualitative understanding about causal graph or actual discovery of the causal graph, how can we use causal knowledge for better scientific practice or better understanding about NLP? So we will first motivate with a general data collection process. There's a famous example of causality during World War II, where a statistician gave an advice about how to make the future aircrafts. So the graph that we're showing here are the aircrafts that return from wars, and the red dots are the parts that it was hit by bomb or whatever weapon. The question will be, how should the future aircraft production enhance? Like, should it enhance? How many people think that they should enhance the parts that the red dots are the densest? How many people think that they should enhance the parts there are no red dots? Great, we have a lot of people who has very good insight on this. So basically, the difference here is that given the same distribution, we form two different causal story. The first one is that these are the parts that we should fix. The other hypothesis is that the plane come back because they survived the war. That's why hitting these parts are not that necessary, are not necessarily leading to the plane falling, but maybe the white parts are the important ones to enhance. So it's basically two different ways to look at the data. Similarly, in our...
Oh, that's very good. Okay, let me just quickly add something here. So you can see, given the same observations, but different causal stories behind the data, you can give completely different answers. Now, let me give an alternative one. Suppose now, basically, every time they just try to target those areas, right? They just target those areas because those parts, they don't care. Yeah, so if you shoot those areas, right, nothing will happen to the aircraft. Suppose that's the case. Then clearly your answer would be, we should put the armor here, right? Because every time, no, they just target those areas. That's another causal story. But now the problem is, which causal story is kind of more plausible? Clearly, this would be more plausible, right? So there's some randomness in kind of where it get damaged, and then given this causal picture, we can infer what have happened to those aircrafts that failed to come back, and then you can make a difference. Thank you.
Great, wonderful. This is a motivation example about how we could potentially look at NLP data. So the direct analogy here is that if people want to investigate for people with mental health, what type of language do they tend to say? Let's say people collect forum posts from people suffering from mental disease. And then which one of the causal graph is more convincing? One could be that the disordered people causes the tone, the topic, maybe different linguistic properties. Or it could be that people who can still be active on forum already maybe are the lighter portion of the mental disease people, and their distribution of language features will be different. So the other example is another selection bias we might see, which is the data of sentiment analysis. So let's say that maybe normally we will expect each item has a certain distribution of being good or bad, then it's positive or negative sentiment. However, maybe for user psychology, at least for me, I would be more likely to post a comment if I have a serious complaint. So potentially, given that the person take the time to write the review, they either have certain personality or they they have a certain distribution of sentiment that motivates them to write this review. That's what's behind our sentiment data. And this is an example inspired in conversation with Maria Antoniuk. The other case is, apart from selection bias, there's also the causal direction of data set collection. So we could say that for a lot of cases, we let the annotator's annotation direction could be from the model input to the model output, or from the desired model output to model input. What are some examples? For example, translation. Imagine that the annotator annotates original German to translate English, but you ask the model to do original English to translate it German, then there are actually somehow a discrepancy here. The other case would be if we collect data, question answering data, there are also two ways: generate question, get answers, versus generate answers first, let people annotate questions. They correspond to different causal graphs. The other case is that apart from the two variable causal direction, it could be that we have more causes than we expected. So normally we think of NLP as from text to certain information, from, for example, toxicity, from text to toxicity. However, for human-centered NLP, we need to care about what writer wrote about this and what annotator judged the toxicity level. This is prevalent in many subjective NLP tasks. We need to care about extra causes that we're missing, but they are in the data collection process. And the correct model should model them. So again, we're really glad to re-emphasize our slogan. The main purpose here in the first part, we completed deeper understanding about real world with causal understanding, and also better scientific practice, taking data collection as an example. In the upcoming part 2, you will receive more exciting examples about large language models and with related topics on interpretability, robustness, and fairness. Thank you very much for your attention.
Well, thank you, everyone. So if you have questions, please come to us. And the next session will be more exciting. Thank you. You are training. Oh, very good. Actually, I didn't know you have
I think we're right on time, just 5 minutes.
Yeah.
And then we have 25-minute break.
Hello. Yes.
For the online participants, we will be back at 11:15 in 25 minutes. Take a good rest.
Oh, okay. I don't really.
Let's come here. Oh, I see.
Blind with that, it was like discuss all the topics about NLP. We weren't really actually. So I was actually asking where is maybe we but it was good. Schedule it. Yeah, I know. The first part. Yeah, I was wondering, basically something that's has to be like poorly by some yeah. And I was wondering, like, can you give it was that like the confidence rate? So yeah, we made a distinction between temporal causality, granger causality, temporal, and stuff that we imagine like the law of physics or of course something very close. An observant that for us this would be the same thing. Existing something. I think still designing the prevention such that people would perceive this information maybe differently to others, but still even though we don't know time frames, that's before and after. Whenever before after these, like within a year, a second, yeah, we can still infer causation. Okay. But let's say this cancer, this typical cancer. Yeah. So the right way you have the observation of somebody is smoking or for the tar, the information will take against. So let's assume you were not involved in the data collection process and you just know this information. And then in your data, you have to you will have people who have cancer. But so basically what you're saying is that it doesn't really matter as long as we can measure, or at least as long as we just know that we have the data for all options. So we have the data collections, not biased in some way.
So we're assuming that, yes, we're assuming that the selection, the data set, like the way we
Yeah, we're bugging me the whole Yeah. This is your problem. Let me try to okay. Let me that so
yeah. Started a post about and I'm also still with visiting.
Okay. And yeah, so what do you work on?
So I'm still kind of in the intersection of developing a program now the way that's more out of distribution and also one direction that we not focused on the HDM and the 3D capacity about is just doing the other direction, using NLP for doing social science, but answering more questions about that.
Okay, so like computational social design, something
like heavier than what NLP people will call science, something where you can identify causal effects, context.
Yeah.
I'm working with a bunch of other scientists trying to listen to these things. Theology, the way cognition is taught, finding about the components of the words, and that being called cognition style on other objects.
Okay.
So yeah, that involved a lot of different stuff, but also the
Okay, that's cool. Yeah, because I'm so collaborating with communication scientists. We have currently a project where we like to we are working on Twitter data, and basically we want to so how these different groups on Twitter like we see like groups of politicians, we have a group of economists, and we have scientists in this how this communication actually has. So they have some social science theory, how these groups influence each other, and but they would like to do some scale up basically their insights into the data. That's why we're collaborating.
That's really relevant. So there's like this branch of text-based like endpoints models.
Okay.
So you know, like big lies, like my postdoc already invented like the model.
Exactly.
So it's usually the way the social scientists work with information.
Yeah.
So the political science variant of this thing is called a beam model. Okay, where you try to take text like on Twitter or whatever and generate on a political scale the position of each individual.
Okay.
You're trying to just like to map people on the line with political opinions. It could also be like dimensional. And there's a text-based version of it. You just do it without, you don't have any voter data, you just have like people talking on Twitter. Yeah, this is called text-based text-based TDIP. And part of the stuff we're doing is trying to like make this model play well for large language model.
Okay.
And ways that you could actually intervene on it, like things to think about counterfactual. Or like how they call it. Like let's say I take a Trump post and I make it into a very Sanders post, but add another context. It's moving into the style space without doing it.
Okay. That's not a problem. So what is the bigger goal? So you basically want to identify causes.
Basically, I have a causal question and then know like whether the reason that people are listening to Trump is because of the policy content or because of the way they talk. And it's very hard to example because Trump has specific topics that you can use about a specific way of saying.
Yeah,
and it's very hard for us to see like which is the thing.
Okay.
And yes, that's a causal question. You could answer. obviously within the space of ideology, keeping the topic constant.
Yeah, yeah. Okay, cool. That's very, very related. So I'm looking. Yeah, but this is, you mean this is something like what the political science use at the moment?
So now this is the way they're doing very like simple. They're NLP tools that are very.
Yeah.
I'm working on one of the goals, like expanding their toolbox in a way that they like things that have like clear principles of market foundation. I mean, they can't just take deep learning out of the box. It's not principled enough. It's very hard to like identify bias and stuff like that.
Yeah.
So I'm trying to do it in ways that don't allow them to analyze this. And not continue this back and forth.
Yeah, okay, okay.
This is
Do you have pretty, do you just about?
well, we have a grant proposal that we got. So we have like now an extended abstract.
Okay.
And a bunch of models that work to us. So it's limited.
Yeah, okay, okay.
It's still working progress.
Cool, cool. Yeah, because it sounds very related. And I'm also, currently our approach is like very standard NLP like, so we're trying, so I'm part of classifying opinions on the Twitter sphere. So stance and I know that these tweets are about measurements to contain COVID-19, but I really like also to get into making some more sophisticated causal claims about what we're actually seeing in the data that would actually very well fit again into their theories, right?
Yeah,
Because then it's
exactly.
more stronger message than just like observing.
I agree. That's the hardness of the task.
Yeah. But it's, I really appreciate that you try to actually make these models work for people who wanna use them, right?
Yeah, I do hope that it's we'll see it. But it's very seeing in person. Physically in like last year's EMNLP.
I was at where you in Dublin?
Yeah, I was.
We met there, and I think I met Roy there.
Yeah.
And now I'm actually starting to work with so trying to get something to work.
That's great. There's a slide here.
Nice. Okay. Yeah, so we will see. Because I was applying the causal NLP stuff to develop the domain annotation for stance detection. There, the issue is just that it's too much entangled. So, you know, in sentiment analysis, you can, I think, separate it better. But in many cases, in stance, a lot of signal is very dependent on the topic you're talking about, right? And
This is I agree. This is the hardest of the task. I'm also
yeah, sure. visual properties of this kind of advantage is this has certain and we are trying to evaluate how our advantage our visual embeddings less than the recommendation. Yeah, that is the new lecture. Then we found the data and train everything on that. It's not any different than the institutional data. So the data is not most
All right. Let's wait. All right. For everyone online, we're now continuing. All right. So hello, everyone. Welcome to the second part of our tutorial. I'm gonna take a really sharp turn from discussing core causality issues into thinking about the ways that it could help us as NLP people. All right, so just to get this out of the way, who am I? I'm a postdoc at Columbia with David Bly. I'm also a visiting researcher at Google. The stuff that I'll be talking about here is kind of vaguely or more than that related to my research. But please come talk to me about that later, and not this is not the topic of this tutorial. So the presentation that you're going to see here right now is based on a survey paper that we co-authored. That's also, I'm going to present it also on Sunday. So if everyone just wants a 12-minute summarization of this and many other things, you should stop by on Sunday. Otherwise, you can hear the extended version right now. So if you don't want to listen to anything that I'll say here today, remember these core arguments that I'll try to kind of discuss throughout this talk. I think that generally causal ideas can and should transform NLP. I will show that they will help us interpret r-dimensional data and models. They could also improve our robustness to counterfactual scenarios. I will describe exactly what I mean by that later on. And I also think they can help us generate fairer models, and at the very least, discuss fairness in a kind of scientific and principled way. However, and one thing that I should mention from the get-go, causality is not a magic solution to all of our problems. The stuff that I will present here, you can think about it as causally flavored NLP or causally motivated NLP. We only borrow the ideas that are useful for us as researchers within our domain. And we can't have guarantees on the stuff that we do without having strong assumptions, as Kun was mentioning before. Still, I think that we should be thinking about doing causal NLP, and I will kind of go step by step showing why I think this is the case. All right, so our agenda will be, I will start out by giving a motivation specifically for us as people that care about prediction problems that involve text, for why you should think about these types of ideas or this tool set that Kon was describing earlier. And I will go over 3 different types of fields or subfields within NLP where this is useful. And I will try to stick to popular demand. It seems that people in NLP are increasingly more interested in doing a principled causal analysis of language models, or specifically large language models, and maybe less interested in issues with respect to robustness and fairness. As I will show, they're all like deeply entwined and entangled with one another. So it's not going to be like a very clean way of separating them. All right. So I'm going to start with a very simple question for all of you. Does Nicolas Cage cause drowning in pools? Anyone thinks yes? All right, perfect. So for us, it's a very easy question, right? When a machine learning model just learns to fit data that it sees across time, could easily be fooled into thinking about this, right? There could be a correlation across time between 2 variables that are that have no connection, sort of happen from many different reasons with respect to the causal graph that we're imagining. But regardless, if we just look at the in-distribution accuracy of like the held out test set from the same distribution and look at the accuracy, results can be very misleading. Specifically, we could have a problem of underspecification where models have very similar in-domain accuracy, but are wildly different in their out-of-domain setting. And this could be because they're using different types of information to make the same predictions, right? We have no reason to think ex ante that models make predictions from the same reason that we would make, right? And in fact, they will often use shortcuts in the data, even stuff that we don't identify, very subtle things. They're just in the way that encoded in the way that we have gathered our data, and use those shortcuts to make predictions. And if we're in the in-domain setting where the shortcut still exists, we would never uncover what our model is actually doing. And it will only be in the case where we change a few things in the world that we will uncover the fact that our model is making predictions from the wrong reasons. All right. So we have many examples for it in NLP. We know that models can easily be affected by sentences that seem very equivalent to us. They can make different predictions in a VQA setting, also to make wrong hiring decisions by using specific shortcuts in the data set that should not hold in the real world. All right. Saying all of this, just to remember, all of us can remember that, sure, deep neural nets, specifically transformers, are really cool. We are all kind of engaged in this ideas and those topics. But we have to remember when we're working with them 3 different things. They are notoriously hard to interpret, meaning that in settings where we care about the safety of our users or people using the downstream predictions of those models, safe deployment is an issue because of that. And second, models can very easily latch onto spurious correlation stuff that we have discussed before. I will mention them once again in this upcoming slides, meaning that they often can generalize to the out of distribution setting. And third, they may be biased, again, from the same problem of the data that they have been trained on. And that could mean that they will be unfair to subpopulations in our data set. The hot take here is that for all of them, there's a way to think about them in a causal way that will, for one, allow us to understand the problem more clearly, and second, propose a way of mitigating the problems that are introduced. All right. So after we have memorized to ourselves at least 100 times that correlation does not equal causation, we can then continue on to actually thinking about these ideas. All right. So if we go back again to the problem of Nicolas Cage causing drownings, we can imagine a very simple case in NLP that is equivalent. So imagine I have this data, and I have annotated it for adjectives in green, figures from one political party in red, from the other political party in blue, and I have a sentiment analysis problem. I'm trying to build a model that reads this text and makes a binary decision based on it. Right. So as we can all imagine, there will obviously be a correlation between the type of adjectives used to describe a specific political candidate and will be within the text. Right. If I would have written this exact same text about a different politician, the adjectives would have changed at the same time, right? It's very easy to imagine such a case. This is because if we have, this is a problem because if we have this biased data, if you have many examples where a specific political candidate receives a specific type of sentiment in the reviews, our model that is learned based on this data could make very biased predictions. All right. So this sounds like a very hard problem, right? Kuhn discussed many nuances, making this problem at many times hard to solve, even impossible in cases. But we have, we as NLP researchers have one ability in our toolbox that many other causal researchers don't, right? If I want to ask a question about the effect of Nicolas Cage on pool drownings, I would have to design an experiment, right? I would have to make Nicolas Cage play in less or more movies and see how this affects downstream pool drownings, right? But in NLP, we have a simpler case, right? We can actually modify either our examples or our models, right? There's no convention that this allows us from doing manipulations or changing stuff within the model, right? It's very easy to imagine cases with people where we can't do the interventions that we would have wanted to do, right? We can't just assume that we can make people smoke less or smoke more such that we can cover causal effects for that. But with models, we actually can. Right, we can manipulate the inputs as much as we want to the training data. We can manipulate the actual model, its representation, and this could actually allow us to answer causal questions about the model in a maybe more straightforward and easier way. Right, so we have discussed before in this previous part about the scientific method. How should we think about this? So one way that we can kind of and a high level think about the way to solve this problem is that we have to hypothesize or suggest some world models, some causal graph. We need to make a hypotheses about the probable causal effects that might happen here. We assign treatment and compare to control, and we get the causal effect, or like the average causal effect across the population. So the example, to answer this problem, we often require counterfactual examples, right? If I had the same exact text, but once it's about Trump and the other time it's about a different political candidate, then I could just input those two examples to my model and get the exact causal effect for that specific word or specific person in the text with respect to model predictions, right? If I have counterfactuals for each specific concept that I can imagine on each specific example on the test set, computing the causal effect on the model is quite straightforward. But generating those counterfactual examples where I change something in the text and keep everything else equal could be quite hard. In the case that Zhijing mentioned before, where I just change one pronoun, this could be, I can solve it with a regular expression. I could generate an entire test set where I intervene on this specific pronoun, and we could all agree that this is fine. But if you can think about more abstract concepts, such as topics or intent or some high-level way of thinking about sentiment, this becomes very hard, right? And specifically in NLP, because everything is entangled within our representation, within our text, disentangling the specific concept from the others or adjectives and the political candidate can be quite hard at times. We are getting really better at this. And if something positive we can take about the recent advancements of large language models is that thinking about generating real counterfactual examples on abstract concept or doing some style transfer is becoming easier and maybe more straightforward. So in the future, as we become better at this, this might allow us to answer causal questions about our models in a quite straightforward way. So there are many branches of people thinking about causally motivated ways of interpreting the predictions of large language models. I'm going to go over all four of them. I'm going to mainly discuss 1 and 2. So maybe the first thing that we can think about equivalating the stuff that we discussed in part 1 and part 2 is concept effects. For once, we can think about high-level concept, abstract concepts that could be latent or observed that generate some text in the world. And we can think about our task as interpreting the model of trying to understand our specific concept changes the prediction of the model. We have to think about the counterfactual under some concept. There are many papers that discuss this type of problem, and I'm going to go over them. Second, we kind of a branch that is very quickly expanding. I'm sure you've heard about some of the works on the mechanistic explanation parts. This is a causal problem where we're trying to attribute specific model components to specific predictions. So I'm trying to uncover the place within a model that a specific fact is arising, or I'm trying to understand where in the model is gender information being kept. And this has a couple of very neat properties where if I do it, I can maybe remove these quantities and get different predictions. I can also maybe do a model compression using this type of causal knowledge. But again, this is a widely expanding field within interpretability, mostly because of the belief that we maybe can't manipulate representations for an entire large language model. There are two other ideas bouncing around where I can think about causal effects with respect to my model. One is training data effects of trying to understand how specific examples or specific concepts within my training data are causing some model predictions. And fourth, a field that is very large outside of NLP, but as NLP people, we have no treatment of it, is counterfactual examples, where we try to understand, given some prediction or for some example, what is the minimal manipulation we can make to this example such that the model will give out a different prediction. All right, so I've mentioned a lot of branches of causal explanations, but right, we know there are many. Right, we have all used LIME or SHAP or any other type method. We know that this is a very large field already. You already know to explain models, right? This is a done deal. And if you look at like the interpretability practice, I think it's like on that room, it's the largest EMNLP and has been for quite a while. However, many of those tools do not distinguish between correlation and causation, meaning that they have a lot of encoded assumptions within them, but they're never explicitly mentioned. And they're mostly ill-suited for thinking about high-level concepts. They usually think about individual words or individual tokens and not about high-level concepts, as we have tried to kind of argue throughout this tutorial. And I think the thing that we should care about most that is problematic within that literature is that they're never compared against ground truth, right? And I think this is something we should keep in mind and repeat to ourselves again and again, right? We think about some interpretability method, and then we plot some heat maps of our words or our pixels if it's an vision case, and we never think about the real prediction under some counterfactual scenario. We don't do that. I will try to argue for why people in causality have been doing that, and how can we think about this to help us do better interpretability. All right, so first, concept level explanation. So from a scientific perspective, it's quite appealing, right? We have some hypothesis and want to estimate its effect on our model. We need to have counterfactuals for it, as I mentioned before, but they're very hard to generate. And specifically, when we were talking about high-level abstract concepts. There is a proposed alternative solution here, right? Because we can actually intervene on our model, instead of counterfactual examples, we can generate a counterfactual language representation, right? If we can imagine another language model, which is the same as our original model, but where we intervened on the representation such that some abstract concept is not visible in there, then instead of comparing predictions on original and counterfactual examples, we can compare predictions on original examples representation and the same examples represented through my counterfactual language model. Right? So we have two different ways of computing causal concept effects on language models. We can either do it through the examples or we can do it through the representation. And again, this is unique to us by because our problem is that we want to understand an organism where we can actually intervene on, unlike a lot of examples where we had humans that we can't intervene on. All right, so I mentioned the word concept quite a few times. What do I mean by it? So anything of meaning that we can think about in the world that can be labeled and potentially you can imagine intervention on. So some examples of concept could be quite a stretch, where it's very hard to imagine if we can intervene on a gender or a race. But at the very least, in the example of text, we can imagine intervening on adjectives, on specific type of syntax. And we can also imagine that we're intervening such that we're changing the domain that a product review is discussing or the product it discusses. And we can also imagine intervening on a text such that it is less racist. Right, this is quite flexible and allows us to think about things that are generating text and measure effects with respect to them. All right. So one thing that is maybe more clear in the computer vision community and less in NLP is that whenever we can generate counterfactuals, whenever we can agree that I have intervened only on the glasses here, and otherwise this example is quite different, quite similar, and should get the same prediction for many classification problems, then I should do that. Right? I have many uses for this, for the ability to do that, but in the case of interpretability, I can very easily understand the effect of glasses on predictions. Right? So it is harder in NLP. Flipping a given concept, given text is still very much a work in progress. And I think that when we can't do it, we can still think about ways of doing that in the representation space. So we can see here some examples of product reviews that are from a specific type of domain, right? The first one is from kitchen, the second one is from DVDs, and I can intervene on the text such that I'm flipping the domain that's being discussed while trying to keep the other things intact, right? I'm only trying to manipulate that abstract concept controlling my domain. So there can be very fancy ways of doing that, but this is what we're trying at least to approximate through some mechanism. All right, you can see that when I have flipped from DVD to airline reviews, the word film is now switched to flight, and the rest of the words are also manipulated such that I still have same sentiment, same general syntax, same general topic. All right, so a couple of things we can do with those counterfactual examples, right? If we can have them for our entire test set, for that specific concept, we can easily compute the causal concept effect. And another thing we can do is we can attribute causal effects to individual model components, right? If I have the same example from one domain, and I have a counterfactual example for the other domain, looking at different activations across the model could allow me to think about where in the model is this type of information encoded. So if this is a type of concept that should affect a large part of the model, maybe this is not very helpful for me, because if I end up seeing that everything in the model is affected by this change, then maybe I didn't learn much insight. But in cases where I'm talking about specific facts or some concepts that should be modular with respect to the other concepts, then this allows me to understand very specifically the type of information encoded in each part of the network. One very cool paper that has now sprouted into like the entire literature on this is causal mediation analysis, where in the case of gender, it shows that very few amount of model components are affecting the prediction with respect to gender. And the way that researchers understand this is through thinking about examples where we have flipped individual gender words within the text. All right, I can, on a completely different note, I can also use these examples, right? If I've generated counterfactuals from my training data, I can also use them for training, right? If I have examples where I have successfully intervened on a specific concept, this is, and I push this into my training data, what I have essentially done is I have encoded my causal assumption within the data. And in fact, if you think about the ability of recent advances in data set collections and data set cleaning with large language models, a lot of the stuff that's happening is that we're encoding causal assumptions through the way that we clean our data and clean our text. So there are a bunch of cool work on that front of using those interventions as examples for our training set. All right, so going back to the examples before with the text about Trump. So we have our problem, right? We want to classify a sentiment given some political candidate, and we have some hypothesis that it could be that the adjectives are driving classification, but it could also be just the only thing the model is doing is reading the word Trump and understanding that the sentiment is either negative or positive, depending on the data set that was used for training. And the question that we're trying to understand when we go about generating counterfactual representations is, can we remove the information about adjectives without affecting the political figure, right? So what we have here is a case where both adjectives and political figures are generating some text, and then we're encoding it in some text representation, and then which is then getting outputted into a model prediction. What we would have want to have is a world where adjectives do not cause text. The only thing that's causing text is our political figure. But this is something that's not possible, right? We don't have this those examples where there are no adjectives in our training data or in a test data, and only political figures are being discussed. What we can do here is perhaps generate a counterfactual representation, seen here, where we are generating it in a way that is not affected by adjectives. So the same examples where I have positive adjectives or negative adjectives or none at all will get the exact same dense representation. All right, so we can imagine cases where we have text classifiers that are being manipulated in a way to do that. So if we have started with a pre-trained language model, let's say we have a BERT model, and it was already pre-trained on Wikipedia. One thing that we can do is we can intervene on that second stage where I'm fine-tuning it. I'm continuing my training on my task-specific data in a way that will remove information about a specific concept from the model representation. Right. So there have been many ways of doing that. A very simple case, as you can imagine, is that I have an adversarial loss in the second stage, where I'm trying to forget some information while trying to remember all of my confounders, right? If I could have done that, if I had a case where the model is trained to not remember the specific type of information while keeping everything intact, I could have had a presentation that does not encode the specific information. All right, so we're now left with the central problem that is obviously usually not thought about in the interpretability literature. We're kind of spoiled in machine learning, right? We're very used to building a bunch of models. They don't have to have any guarantees because the only thing we care about is some accuracy metric on a held out test set, right? We have some model, it has some accuracy on a test set. We can take another one and just compare numbers. And if one number is larger than the other, then we say, cool, we have a new state of the art. The problem with causal estimates is we don't know the actually true effect, right? We never observed the same exact person that did not receive the treatment, right? This is never revealed to us. And this is kind of the fundamental causal problem. At the very least, when we think about problems in interpretability, we can try to convince ourselves that what we estimate, that any interpretability method that we can generate, such as the one that I mentioned before with the representation, uncovers some ground truth ATE, some true average treatment effect. And maybe a good way to approach this from a causal perspective, is that we should generate more and more test sets that include counterfactuals, either through some human manipulation or some model that we can agree on and done a decent enough job, right? If we can compare any method to some ground truth effect, like the actual manipulation that we have done in the text and compared predictions across a test set, maybe we could at least make some advancement towards understanding which of the interpretability methods is actually capturing complex effects in the data. All right, so another field that relies on those examples and counterfactuals is the work on mechanistic explanations. Again, those counterfactuals allow us to identify where information is stored within the model. And using that, we can identify causal effects of each example, right? I've discussed this before. This has vast implications, right? There's a reason. I don't know if you have read the Rome paper, or the causal mediation analysis paper. I highly recommend you do it. This allows us as NLP people a couple of paths to continue by using this causal understanding. So let's say we have identified which model components are using a specific type of information. So we have identified all of the activations or of the neurons within our model that are in charge of making predictions or modifying predictions where gender information is revealed. If we have that, we could remove or edit this information and debias the model. We could also remove this information, making our model robust to changes with that attribute, right? If our model is not using gender information, then in the test set, if gender information is correlated in a different way with some predictions, my model will not be using it, making my model very robust to those counterfactual scenarios. And thirdly, we can also imagine a way of compressing the model if we have identified neurons that are not useful and from a causal perspective, or that are using information that we would not want to use when deployed. So all of these cases rely on us being able to use those counterfactual examples to identify specific causal components that the model is or not using. There is some strong assumption in that literature that those model components can be disentangled, which might be problematic if you recall Kuhn's part. But again, if we can agree that this assumption is realistic in many cases, then there's a lot we can do using that type of knowledge. All right, another kind of fastly growing field is trying to understand the causal effect of training data. So now that we have a world where models are very, very large and we don't understand the data that they were trained on, one question that we could have is whether the prediction that we're seeing is a cause of some memorization that occurred within the training, some specific example the model is using, or specific concept that was encoded during training, or is it some generalization abilities that we have essentially successfully encoded in the model. So this is still quite young, but some very interesting questions that we can have there is trying to understand under some intervention, where an intervention is removing or adding examples to our training data, how would those my new model's prediction would have looked like if those examples were in my training data, right? So I can understand the causal effect of adding some type of information and encode it into my model. And lastly, on the explanation front, I've mentioned this before, but a very common way to think in an intuitive way about what my model is doing from a causal perspective is trying to understand what manipulations would I have to do to my given test set example such that the model will output a different type of prediction. So let's say I have some this exact text example with the political figure and the adjectives. Let's say I'm now trying to change the information slowly but gradually until I get a different sentiment from the same example. If we follow a specific causal graph, we can maybe ascertain what is the effect of specific concepts on my model, right? If I change some of the adjectives, let's try and change more and more adjectives. When does my prediction change? When I try to manipulate the political figure, and I go across some political spectrum, how far do I need to go until prediction is changed? All right, so this is very common with tabular data, maybe the most common out of the four I've discussed. But in NLP, for cases that I think are like seeing your faces, I see that are intuitive. It's quite hard to imagine, right? We have a very high-dimensional data, and trying to traverse it in a way that is meaningful can be quite weird, or maybe non-intuitive, right? Maybe in the political figure case, it could be intuitive to imagine that I'm slowly moving from the rightist to the leftist political figure and observing my predictions as I change. But if, let's say, I change something with respect to syntax or with respect to style, I want to see our formal language is affecting my predictor, it could be very hard to imagine traversing in that space or making it gradually more Shakespearean or something like that. I'm not saying that this is impossible. I think there's now a lot of cases in NLP where this might be the case. And maybe this is a call to action for people to take this type of ideas from general machine learning research and into NLP. All right, so to conclude the part on explainability, deep neural networks, we can think about them. This is a mental thought experiment, not a real thing, right? There are functions, but we can also think about them as organisms that we still don't fully understand, right? We're using them. We're training them, but we don't know the exact specifics of for why they're making specific predictions. Because this is a recognized problem, explainable AI is everywhere, right? It's a huge field. It's still growing in NLP and outside, but it adds a lot of explicit assumptions about what is driving, what is confounding the type of information that we're seeing in the model. So we can take the scientific process and make hypotheses, design experiments that test those hypotheses, right? I think for this reason, and from a high-level intuitive thought, I think that model explanation is a causal estimation problem. And in fact, it's a relatively easier causal estimation problem because there's a lot in our toolbox that we can do because we can manipulate the organism that we care about. All right. So to answer this problem, we often need counterfactuals. But even if we don't have them, we can still imagine interventions on the representation space such that we can still compute approximates for those counterfactual quantities. All right. Again, so moving on, another field that is maybe even larger or at the same amount of size within the machine learning community that does not receive the same treatment in NLP as robustness, and specifically the causal perspective on robustness. We are growing increasingly concerned in NLP. This is also true with spurious correlations, right? This is a buzzword that has been kind of pushed around in this talk, but also in other cases. But from a causal perspective, we can think about this very clearly. So when we have some factor, environment, domain, there are many ways of thinking. It could be some nuisance that is informative in the training data with respect to both the features and the label. And this same environment, the same connection between this E and Y is not guaranteed to hold in test set. So it could be that we have in our training set, right, the canonical example, we have cows on the in our training data, we have cows in their natural habitat. We have a bunch of images of cows. They're all in the background. We can see grass because this is where cows live. We train our model, learns the very obvious association that grass causes cow, right? Because every time it sees a model with an example where the classification should be cow, the data, the sample shows grass in the background. And we could have a model that learns this association between grass and cow. But when we go into a test set where we have cows on the beach, the model would have no way of understanding whether this example is still a cow because it's not using the actual cow features. It's just using background features. If we again recall our same sentiment analysis example, we have successfully estimated the effect or the causal effect of adjectives on our classifier. Right, but we still have a biased model. We still have a model that is using adjectives or not using adjectives for predictions. And also, there are parties in political systems that we have never seen. Right, our data set is bounded by our ability to gather and clean the data. Right, there's stuff that we haven't seen, also stuff that did not exist when we were training the model. Even the same party that we're observing could change over time, right? It could change beliefs and stuff like that. And the question this literature asks is, can we generalize when this information changes? Can we learn in a way that is not using this domain-specific information? Maybe can we learn a sentiment classifier that is not using specific individual names and just using the actual content of the text? Can we use this type of tools to build a model that only sees a cow and does not use the background when making predictions? All right. So this problem is also called out of distribution generalization. And the main idea is that we want models to perform well in counterfactual scenarios. So say I intervened on the background. I've now put the same cow. I've taken it myself and put it in a beach setting. I would still want to make the same correct prediction. And the reason I highlighted that we should fear that in reality is also called under specification, where very similar in domain accuracy could be observed for different models, but their out of distribution accuracy could be wildly different, right? So we should be very careful when just using the information, the same distribution that we observed in training, because this could hold the same type of shortcuts that we would not want our models to use in deployment. All right, so let's think about this from a causal graph perspective. So imagine that the word Donald Trump causes a sentiment to be negative, meaning our model will end up using the type of party affiliation as a type of information that is causing negative sentiment, and this is a spurious correlation, right? We want our sentiment classifier to use the actual content of the text and not a specific name that we're seeing in training. So we can call this type a type of spurious correlation. Specifically, it's anti-causal because sentiment is causing this type of, right? So text is generated after we have some abstract concepts. All right. So if our model is using this type of information, if Donald Trump causes negative sentiment, This means that we have no way of understanding what is the maximum risk that our classifier will show in test time, right? There could be, our model could be using this type of information to any magnitude possible, and this could cause as much harm as possible in training. We could have a classifier, a binary classifier with 0 accuracy by doing that. All right, so we can imagine a causal graph for this type of scenario, where we have some environment variable, right? We have some domain, we have some political affiliation, we have something that causes both the causal part of the text, the part that is spurious, and only the causal part generates Y, right? So the only thing we want to keep in the text is the information that is actually describing sentiment, and not the information that is just correlated with sentiment. So this quite general setting could be used in any case where we're imagining different chunks of text being affected by specific or other concepts. And the solution for this type of a problem, or to solve this graph in a way that does not use information and only uses the X causal or X anti-causal non-spurious to generate prediction, is called invariant learning. And I've asked GPT-3 to give me an answer for why what this is. So this is actually not exactly true, but true enough for us to understand. So generally speaking, we're trying to think about 2 types of information. All right, there is information that under any environment, or you can think about this in the sentiment analysis case, every domain holds the same information. So positive words are because of cause positive reviews, right? This is true in every case. But there are examples in specific domains, such as individual words or specific products at a specific domain, that change across it, right? And what we're trying to do is remove the information that varies across environments and only maintain the information that is stable, right? We're obviously losing information from each specific domain, but what we're getting in exchange for that is a stable model that under any intervention to the domain will give the same prediction. All right, this is loosely by GPT-3 called invariant learning. So there are 2 things that we can do here. From an observational causal inference perspective, we can enforce condition on the learned representation, right? We can derive some conditions from this causal graph and try to encode them in our learning objective. For example, we can understand from this graph that to have a representation f of x that is not using the spurious information, if we have had that, then it would have been conditionally independent. Then we would have had this condition independence condition where Y is independent of the environment given that representation. So one thing we can take out of this idea is that maybe we can take some condition independence test, push it as a regularization term in our learning objective, and make sure that we're generating representations that at the end are enforcing this condition independence test. Alternatively, from the interventional perspective and recalling our ideas about interpretability, we can generate counterfactuals with respect to the spurious features and add them to the training data. Right? If I could have generated examples where I have cows on the beach, then obviously there will be, and I would have done that for every examples where I have cow on grass, there will be now no correlation between the background and the prediction of a cow. Right? If I could have done that, problem solved. I can just shove this all into the training data, and I will already have a model that does not use this shortcut to make predictions. This is obviously very hard, especially when we don't know the type of spurious information that our model is using. All right, so this sounds like a very hard problem, right? So trying to learn a representation without knowing ex ante what is the spurious information, while optimizing in a way that ends up having some representation f of x that is stable, is really hard, right? Where just to begin with, trying to enforce conditional dependence is a very hard problem in statistics and machine learning, but we are conditioning here on a continuous variable, right? We're conditioning on the prediction of our model, but this is also the target of our optimization problem. We want to get a representation that satisfies this problem. right? So maybe because it's hard, maybe because it's interesting, maybe because it's important, in machine learning, this problem has become quite central. Just as a show of hands, anyone has heard the word IRM? IRM, all right, 3 N's, all right, perfect. So I think NLP people should be more aware of that literature, and I'll try to expand it. So for the past, let's say 5 years, the community has kind of been obsessed with this idea of learning representation that are invariant to some environment features, and we have had some limited success so far. Some things have worked better than others. We can think about this in a way that's complementary to the domain adaptation techniques in NLP. Where in domain adaptation problems in NLP, what we're trying to do is we're trying to learn a way to move between domains, right? We want to keep all of the domain-specific information, but we want to be able to use it in test time, right? So we're keeping all of the spurious features. We're not removing any of them. We're just hoping that in test time, we could map the example to the correct domain in training. And in a space where we are increasingly learning more and more domains in training, right? We're expanding the type of data sets that we're using for training. This could be fine, right? We could still have a test case where we've actually seen examples in that space and make correct predictions. But then again, if you probably have seen with basically all of the community playing with models type of ChatGPT, every prompt generates essentially a new distribution, and we could always have environments that we have never seen, examples that we have never seen, and if the model is making predictions using some shortcuts, they will be uncovered, making our models look bad in many cases. So there are many alternative solutions to thinking about ways of generating a representation that is invariant to some environment variable. I will discuss one thing that I've been working on, but there are many different ways. So this is not even a complete list of solutions. I think many of them could be very easily used in NLP. So far no good. So far people have not been using it. I can, for example, which case could be actually useful here. All right, so one thing that we can identify is ideas from domain adaptation, which we are using, but many of them, this is not the case. All right, so before I go into a specific method, so we can think about the ways of actually doing that, some caveats. So robustness is not necessarily a causal problem, right? It's just a problem of trying, if we could just think about this as machine learning people, we're just trying to make better predictions out of distribution, in whichever way we define out of distribution, right? Causality here is only a way of thinking about how can we understand this problem? How can we model this problem? And how can we take solutions from fields that have already thinking about these types of problems to generate better solutions? We're still measuring ourselves here in the same way that any NLP model should be compared against, right? We care about some predictive accuracy, right? So what I'm saying is, if this doesn't work, then regardless of the fact that causality helped us generate the solution, we still shouldn't care about this that much. But if we do generate a solution that is useful and is based on some principled ways of thinking, or specifically a causal way of thinking, then we have a lot of insight of how to improve this, where this is going wrong, and how to build further. One thing that causality can help us as machine learning people is try to rebuild this cycle of using empirical results and theory in a way that's informative for one another, right? Because if we have generated some result here, we can understand why it's happening. All right. So I've mentioned that there are multiple ways of thinking about this, right? We have a very difficult objective, trying to remove this type of information from our presentation. One thing that we can do is instead of thinking about this bi-level optimization, we can just think about calibration across our domains. So one way of thinking about why is this desirable, why would we end up with this type of a solution? We all know that deep neural network specific classifiers in NLP that are fine-tuned are very overconfident, and that very small perturbations to test examples could lead to very different predictions. And And one thing that we have kind of a hunch that works in many predictive examples is that models that are calibrated should be something that we want to have. Specifically, if we think about multi-domain calibration or having models have the same level of confidence about their predictions across multiple environments, could lead to a model that is not using environment-specific information. Right? So from a mathematical perspective, we can directly see it. If we have a model that is calibrated on every environment, this leads to conditional dependence. However, getting into that place is not that straightforward. So let's think about, again, two examples from our same politicians. We have tweets from a lot of them, and we have a bunch of examples for where the model thinks with 90% chance that this is a positive example, right? If we had a case where for some distributions, or for some environment, the true probability is only 80%, and for some it's 100%, but the model thinks that they're the same, there's a good chance that our model is using specific information from the environment to make those predictions. So if we know that, there's a lot that we can do. Specifically, unlike all of those methods that I have kind of briefly mentioned, we have some abilities. We know, like also in NLP, we do a lot of stuff to make sure our models are calibrated. And if we can try to enforce this type of calibration of like having the same level of calibration across different environments, then we can generate invariant representations by only using one extra variable, right? The only thing that I would have to do to make sure that this is equal in training is use that variable telling me the politician from which this tweet has arrived, and trying to enforce this condition in training. Right? We have many ways of making sure deep neural nets are calibrated during training, and this might be a way to mitigate the problem that we're trying to solve. All right, so this is just one example just to help you think about how do we do this type of work in a principled way, such that we can build causal ways of thinking about distribution using a type of objective where we enforce calibration across multiple environments. We can get models that are more stable and are better in out-of-distribution settings. All right. So this is one example, but there is some takeaway here that is quite true for most of them. All right. If we want to be able to generate models that are stable across some interventions on some environment, there's some things that we can do. We can specify how those distributions may shift at test time. Are we expecting label shift? Are we expecting covariate shift? What is the type of change that we want to be guarded against? What are we expecting to happen in test time, in deployment, that might change in comparison to what we have trained on? All right. Our personal preference, or my personal preference, is to use causal graphs. This is not necessarily the solution. As we said, this is a prediction problem, but they could be very informative, especially when we're thinking about metadata that we have alongside our text, and the way that it interacts and ends up generating text. After we have built our world model or mental model for how does this world operate and what are the changes we expect might happen, then we can derive a suitable learning criterion or suitable learning algorithm that will enforce this. One way of doing it directly from causal graphs is thinking about the invariance like the independence conditions that should hold such that my representation is not using unwanted information, and try to enforce this condition independence on my model through some regularization during training. Right? It will be agnostic to the model, but we are manipulating the learning algorithm. All right. So this field is as I said, is vastly expanding, and there are a lot of trends and directions that are also relevant to NLP. One thing that's also relevant to what Zhijing talked earlier about the causal direction of the data is that if we have some understanding about the way that our data is being generated. So for instance, sentiment causes text, right? But helpfulness of a review is caused by the text, right? We have the first is an anti-causal problem, and the latter is a causal problem. Knowing that direction should tell us that different conditional dependencies should hold, such that we have a stable representation. But each one of these types of problems should lead to a different regularization scheme, right? Because different conditional independence arises from each of those conditions. And if the only thing we're doing is that we're shoving into our learning scheme the conditional dependencies that should hold such that this representation is stable, then each type of problem would induce a different learning algorithm, right? So this is a very clear-cut way of where causal knowledge informs a different learning objective that then affects the robustness of our model in out-of-distribution settings. All right, so I've so far discussed kind of classification problems, which is very common for like out of NLP. This is often the case that people will look at, but we are increasingly more concerned with doing the same thing with text generation. So you can take this type of objective where you're trying to remove spurious information during training with respect to some environment, and just do the same just with a language modeling task, right? We can have texts from different type of environments. We can have Wikipedia text, we can have Twitter text, we could have some code, and try to remove information that's specific to an environment. One thing that you should think about when I'm saying these words is this is often useless, right? This is when we prompt GPT-3 or whatever model, and we want to get some answer. This using some specific environment-specific information is a feature and not a bug. Or maybe in a different way, think about this: having a model that is not able to use Wikipedia type language as opposed to Twitter-like language, has no understanding of the differences between and tweet about some subject and a Wikipedia article for it, is not something that we will want. All right, so maybe in the context of text generation, it's very hard to think about the usefulness of removing this type of environment information. But one thing that I still think that we should devote some time to, and we have not done this enough in this talk, but I think generally this is true, is that invariant text generation can still be useful for many social science applications. Let's think about one example. Right? Let's say I want to test the amount of the change in voter outcomes because of the way that a specific politician speaks. So let's think about some political speech as composed of some content, some policy content, and a style of the speaker, right? Let's say I want to test the effect of that style on some voter outcomes. Right? One way that I can help political scientists to understand, or we as NLP people can think about solving this problem for them, is that if we can generate a language model that does not use style to generate text, or can generate text in a style invariant way, then we can give those two examples. We can take a speech from some political candidate, generate a counterfactual where there's no style specific information, and then take those two examples and see how they affect people in the real world, right? We can have a controlled experiment where we have used those two types of language generation capabilities. All right, so just to wrap this up, it's not that useful for us within NLP, but still invariant text generation could be something that we can do to help some scientists interested in text. However, if we think about robust controlled text generation, then we have a very clear-cut way of using causal information to make better predictions. All right, so in fact, the problem of control generation, like generating, for instance, non-toxic text, can have a very straightforward description from a causal perspective. All right. In fact, the hardness of doing control generation under distribution shifts, under some changes to the data, is in fact a problem of learning an invariant classifier to that controlled concept. All right, so let's think about this for a second. So let's say we have some text denoted by X, and we have some target attribute, right? We have some toxicity, the toxicity of a text. And our goal was to generate, parameterize our language model in a way that we're generating only text conditioning on having non-toxic content. All right, if we just use Bayes' rule and we flip this, we understand that to generate this, what we need is to have some P of X, like the distribution of language, and the probability of a text being toxic given that text. And if we have a binary classifier for toxicity, then we can, one thing that we can do is we can just filter examples that are toxic from the what our model is producing. In fact, models like Lambda are doing very similar things. Right. So if we decompose this problem, there are three terms that we should be interested about. One is the toxicity, whether a text is toxic, the probability that the text is toxic, and that control distribution of generating text under not generating toxic content. And if we just replace that identity function with our loss, then we can immediately see that if our test distribution is different from our training distribution, the predictor that minimizes our risk under that distribution could be very different from the optimal one, right? So if we have a toxicity classifier who's very correlated with the topic, then if we change the topic, let's say there are some topics that are more toxic, right? If we talk about gun control, then we have a probability of toxicity that increases. If we now have a model that uses or conflates the topic with toxicity, when the topic changes, our ability to generate non-toxic content could end up us only generating text on non-toxic topic, right? It could be that the model is not capable of now generating non-toxic content about highly toxic topics, or anything else could happen. Our model could just generate very bad language there. It could generate just incomplete sentences. We have no way of disentangling the specific controlled concept and everything else that's correlated with it. And we can use the same exact objective that I've shown in the prediction case, in the classification case, to make sure that we're generating a predictor that is invariant to those changes. If I have done that, then I could now in test time use my invariant predictor to remove examples that are toxic, but still be aware that they could have a topic that is correlated with toxicity. Right. So if we kind of just summarize this, there is all right. So if we can decompose a conditional generation problem into a classification problem and a generation problem, we can think about the classification problem in a causal way and generate principled solutions that are allowing us to generate text that is controlling for some attribute while being invariant to changes in our training data. All right, so to conclude all of this robustness stuff, there is an emerging set of tools for reasoning about distribution shifts and deriving robust prediction rules. There are some tools that are very simple, right? Like calibration, what I've presented, that suggests that there's a lot of potentials for those tools to have impact also within NLP. There is still a lot of rigor needed in solutions about out-of-distribution generalization, and causality could be a way of thinking about how to derive those types of solutions. And in some cases where we have not thought about this before, like control text generation, this is a very direct use for this type of methods. All right, so I want to I'll go very briefly about on fairness. It's in fact a problem that shares a lot of the same modeling tools as robustness, and it has been quite studied in NLP. So there have been many attempts to measure the fairness of predictors in NLP. We can think about as predictions change, as we change some protected attribute, as we change gender, and more nuanced way of like changing the prompt and seeing how the model behaves given that we have changed. I'm sorry, some protected attribute. So by now, this should be very straightforward to you, that if we have some bias in our data, it'll be very easy for those models to inherit and even amplify those encoded in the training data. And that there's a very simple way to think about this in causal terms, right? I think Zhijing mentioned it before. If we think about a notion of counterfactual fairness, maybe one thing that we want our model to have is that given that we have some example, we change the gender, but we keep everything intact. We want our model to be unaffected to that manipulation, right? So if we can imagine an intervention on gender in our text, what we should want to enforce is invariance with respect to that intervention, right? And there is a very clear causal language to describe this idea, and we also have a bunch of methods to try and enforce this, right? I've mentioned domain in a bunch of different examples before. A domain can now be gender, right? If there's one protected attribute, and we call it gender, and we train in a way that ends up having independence between that variable and my learned representation, then I've generated a model that is counterfactually fair. All right, so there's very obvious connections to those two ideas that we have discussed before, right? Robustness, we can think about an environment as that protected attribute, or interpretability. We have some attributes, some concepts that are affecting predictions of the text that we don't want them to have. And so basically we'll find some causal effect on our model, but it's not desired. Right? If we have in the interpretability part, if we have identified this type of effect, we should now think about ways to make sure it's not there when we end up learning a new model. All right, so just highlighting a bunch of cool stuff that has been done with text. So there's been some very interesting work trying to show that causal analysis is required to determine the actual fairness of an observed distribution of data. There's a lot of metrics for fairness that we're using that can be motivated from a causal perspective. And that counterfactual fairness is also a very useful notion to think about fairness and how to enforce it in training. I mentioned this in the beginning. There is a bit of a definition problem, maybe a philosophical problem of, right, what we're trying to approximate here is trying to think about an intervention on some abstract notion that is generating text. But if this attribute is gender, it's going to be very hard for us to imagine what would that intervention be like, right? The example where I put cows on the beach is something that you can imagine me doing. But an example where I've changed your life story in a way that changes your gender, but everything is the same, is quite hard for us to imagine in the world, and also hard for us to imagine that being shown in actual text. So the hardness of imagining interventions on an attribute makes it a bit tricky to think about this, its effect on text representation models. All right, there is obviously some fundamental connections between fairness and causality and unfair bias, and it's for many obvious reasons it's been mostly studied in the low dimensional tabular data case, but there are some cases in NLP where people are gradually more thinking about this, and I invite you all to do this more. I think there's a lot of room for people from NLP thinking about how abstract concepts affect many different parts of the text and not just individual words. And again, this is a hard problem, and it needs to be studied with more care. Yeah. All right. So to conclude this part of the tutorial, there are many different ways that we can think about very important and hard problems in NLP, where causally flavored solutions might allow us to generate better solutions. It's not that the problems are necessarily causal, or that their causal explanation is necessarily the best one, but there are problems where thinking from a causal perspective could allow us to model the problem, propose solutions, and think about this loop of how this affects the capabilities of our models. So at least in the case of interpretability, robustness, and fairness, I honestly think that there is a lot from this toolbox that can help us generate better and trustworthy models. Thank you. All right, so we have a few minutes to questions, but let's take everything offline. We can just whoever has questions, you can just